big bulk. This volume is N plus heavily doped material. This is a SiO2 material, silicon oxide material. It is basically insulating material, dielectric material to have resistivity. And on top of that, this brownish material, it is aluminum or metal, and to which this gate is the terminal. As we know, what is the operation of the MOSFET when we apply a voltage to this gate or N device? Since all are as in the VLSI field and the topic is advanced devices, therefore, since it is a basic device of MOSFET, I will go through this device very quickly. When we apply positive voltage on this gate, because of the inversion process, capacity effect, the charges induced in this P substrate in this channel length L are the negative electron charges, and that is development of the channel. And when channel gets developed, current can flow from source from this bulb through this channel to drain, and in this way. In this way, the device, the MOS transistor is switched on. Then once device is switched on, then what happens here? The same view once again shown here in detail. SiO2 gate oxide, it is good insulator whose permittivity, epsilon R, permittivity is approximately 3.9. And this is P body, this is channel length, the structure of MOSFET. Channel length itself is referred as feature size or technology node. Technology node, many people call it only it as a technology or only feature size or only feature or the current technology trend. These all words are synonym to each other. When somebody says that the node is of say 4 nanometer, it means the transistor has a channel length of 4 nanometer approximately. This is the meaning of that. Keep always in mind, technology node or feature size means nothing but the length of the channel. Width of the MOSFET or width of the channel can vary, depends. That depends upon how designer prepares his layout, W by L ratio, and the sizing of the devices and all. It's different area. But normally in case of digital ICs, when there are billions of transistors manufactured, fabricated on one IC, normally in case of digital, all the devices have got same channel length called as L, that is feature size or technology node. Okay. Then what is mean by when device is off, cut off? When device is off, it means gate to source voltage. Gate voltage with respect to source is less than threshold voltage VT. VT 0. Okay, when there is no substrate coupling, substrate bias. Then drain current ID is equal to 0, because since gate voltage is not there, channel is not induced here, and drain current is equal to 0. Okay, it is ideal thinking. Ideally, drain current is 0. Practically, drain current in picoampere called as leakage current always exists. Then, when the gate voltage is more than threshold, but the drain to source voltage is less than VDSAT. VDSAT means VGS minus VT. It is typical mathematical term. Since the audience is from VLSI, they are well aware of what is meant by VDSAT. In this way, when gate to source voltage is less than threshold, but the VDS is less than VDSAT, that time channel is induced and electrons move from this, in this way, from the source N plus through the channel, entering to drain and going to the positive polarity of the battery. This is the electron current. Means conventional current is what we normally do in the mathematical way. It is from positive to negative, and drain current ID flows. This region of the MOSFET is called as linear region. And in this, as mentioned here, the MOSFET behaves like a voltage controlled resistance in this, because by varying the gate voltage, by varying drain voltage, we can vary drain current. When you vary the VDS, drain current immediately gets varied, and that is called as linear region or voltage controlled resistance. Okay, the most popular region is the next region called as pinch off region, or later on called as saturation region. In this region, now the turn is same. VGS is greater than VT, and now VDS is equal to or greater than VDSAT, means VGS minus VT. Once this happens, then in the saturation, this is the shape of the induced channel. Because of higher VDS voltage, because of higher drain to source voltage, the electric field between the drain and source, the electric field is always called as the voltage divided by the length. If the voltage between drain and source is, say, imagine 5 volt, just imagine 5 volt, and length of the channel is equal to, say, 1 micrometer, 1 micron, then 5 volt upon 1 micron becomes 5. If that micro goes up, it becomes mega, 5 mega volt per meter. That means the amount of electric field induced in this channel is really very, very high. Because of induced channel amount of electric field, the channel gets suppressed from the drain side, and the process of pinch off and saturation starts. When we increase the value of VDS beyond the value of VDSAT, then this point of pinch off will move towards source because of the high electric field available from drain to source. That will put restrictions on the drain current, and drain current IDS starts remaining constant. That is mentioned here. See, this is the condition here. The channel is pinched off here, but the drain current exists there, and drain current is almost constant, remains constant, ideally constant. Practically, some inclination is there, some incremental uh, change in the current is there with respect to VDS. The same operation is mentioned here in basic equations, which everybody knows very well. The first, when VGS is less than threshold voltage VT, no doubt device is off. Drain current ID is 0. Non-conducting region. When VGS is greater than threshold voltage VT, but VDS is less than VGS minus VT, means VDSAT, then it is linear region, just now we discussed. And drain current ID is given by, this is called as beta, normally called as gain factor beta. Beta into VGS minus VT into VDS minus VDS square by 2. In this equation, if mu is the mobility of electron, listen very carefully. This term is very important now throughout the presentations. Or all future devices are based upon these fundamental equations and the mathematical terms, physical constants available here. A whole invention varies through these equations only, around these equations only. Mu is the mobility of electron in meter square per whole second or centimeter square per whole second. What is mean by mobility? Okay, well, better way we'll discuss that in the next slide. Let's here our aim is to go for the equation of ID. Okay, mu is the mobility of electron. Epsilon OX is the permittivity of SiO2 material, oxide material. POX is the thickness of oxide SiO2 material. W by L is the aspect ratio of the device, called as width upon length of the MOSFET. VGS, we know, get to source voltage. VT is a threshold voltage, manufacturing constant. VDS is what we applied, and this is the equation. This equation has got advantage as well as disadvantage. If we want to use the device in as an amplifier, then normally the amplifier in the transistors are kept in or ensured in saturation region, and we do not want, really we do not want that ID should become the function of VDS. We don't want that. And what is happening in this equation? ID is function of VDS also by these two terms, and ID is function of VGS also. Since ID is function of VDS also and VGS also, it's not good. That is giving, there is a complete paradox. We expect the MOSFET should behave in such a way that drain current should be controlled only by the gate voltage. That is what transconductance, that you expect, if the scientist expected that BJT or the MOSFET everywhere, the output current should be controlled by some input parameter. In case of BJT, the output current, collector current is controlled by the input base current, and in MOSFET, drain current ID is to be controlled only by VGS and not by VDS. But that is happening here, VDS as well as VGS. This region is no doubt, it is useful region in some applications, but in analog circuits, low frequency amplifiers, high frequency amplifiers, RF amplifiers, LNAs, mixers, VCOs, local oscillators, in these all analog devices, analog circuits, Normally we expect saturation region, and linear region is not expected there. Therefore, more important is the next called as saturation region now, where now in saturation region VGS is more than no doubt VT like this case, and VDS is greater than VGS minus VT, saturation region. This is the excellent thing what is happening now. See, ID is same beta, but beta by 2 here. This two second number term 2 is there. And there is simple bracket VGS minus VT whole square. Since VT is constant, W by L is constant. If some oxide material, TOX and mu are constant, it means ID is simply proportional to VGS. Drain current is simply proportional to gate voltage. So this is the expectation from the MOSFET it should behave. Output current should be controlled by the input voltage and not by the output voltage, not at all by VDS. And that is really happening in this third region called as saturation region. Okay, all right. These are the three equations of the MOSFET based on which the further theory depends on. So this is same thing is once again mentioned. This is the drain current ID in saturation region called as beta by 2, VGS minus VT square. There is actually, the equation is this also. It has a one multiplier. This multiplier is ideally equal to 1. Second term is 1 plus lambda VDS is modulation parameter for the channel. And this lambda value is ideally 0. And if lambda is 0, bracket value becomes 1. And the equation remains the earlier equation of the previous slide. Okay, this is the same figure explored here slightly in detail to make you aware. N plus, then P substrate, again N plus, and the channel and how the pinching of saturation happens here. Fine. This is the characteristic purposely mentioned here, higher voltages to make you comfortable. In case of P device, when the gate voltage is more and more negative, we get here more and more drain current. And this region, this horizontal region, is called a saturation region, where there is an increase in VDS. Look at here. VDS is increasing drastically. Enough amount of voltage is applied. But still, with respect to VDS, there is no change in ID. Look at this horizontal line, this line, this line, this line. For example, this line shows that drain current is constant nearly at say 6 milliampere, and it is dependent only on VGS, which is minus 8 volt. It is completely independent of VDS. This is called as saturation region of the MOSFET. In BJT, we used to call it as the active region. This also is called as active region, but in MOSFET, it is saturation region because of the channel is involved. It is all about the device. Now, this is all about the simple theory of the MOSFET, where the whole VLSI world is working since more than 40 years. And MOSFET is a quite mature device now in the market. Almost the complete market, commercial market, more than 99% really is captured only by the MOSFET. All the ICs are made up of MOSFETs. These are the physical constants. Purposely, we are exploring. We shall spend some time on this slide, and then we will go to the advanced devices other than MOSFET, which are very famous in modern electronics and industries now. Look at the first parameter, the mathematical parameters or the physical and material constants. Boltzmann's constant, no doubt the name of the scientist, which is 1.3 s 10 to minus 23 joule per degree Kelvin. Okay, fine. It is a physical constant. Electronic charge on one electron is 1.6 10 to minus 19 coulomb. Thermal voltage, or it's also called as a volt equivalent of temperature, which is kT by Q. Actually, this is the very famous Einstein's equation, dP by mu p, diffusion constant by mobility of electron, and diffusion constant for hole, that is again electron dn by mu n, dP by mu p, is a thermal voltage, which is given by kT by Q, or only kT, depends upon what is the value of Planck constant, and which is called as Vt, which is nearly 26 millivolt at room temperature. Thermal voltage. Keep this figure in mind, because new devices use these values in the invention, and why the devices are popular. Their all answers will lie here. Next is energy gap of silicon. It is approximately 1.1 electron volt at room temperature. Energy gap this in the fundamentals of physics we learn it is the gap between the conduction and valence band, which is nearly equal to 1.1 electron volt in case of silicon. All right. Dielectric constant for vacuum, free space constant, epsilon zero, permittivity is 8.8 picofarad per meter or 10 to minus 14 farad per centimeter. Keep this in mind. Free space, the free space when there is no material, this is the value of constant called as epsilon zero. Dielectric constant for silicon is 11.7, nearly 12, approximately 12. 12 into epsilon, this epsilon zero. Forget epsilon zero. Just keep in mind that silicon has dielectric constant is equal to 12. And vacuum has dielectric constant epsilon r is equal to 1. Okay, fine. What is the meaning of this dielectric constant for silicon and for TOX? Let us explore slightly in detail. Dielectric constant for silicon dioxide, SiO2 layer, which just now we have seen, on which gate is developed or manufactured, is epsilon OX, means oxide layer, is approximately 4, 3.97. 4 into epsilon 0 farad per centimeter or farad per meter. Keep this in mind. This is 4. Silicon dioxide has got permittivity or dielectric constant or the value of K, many people call it as K, or epsilon OX is equal to nearly 4. Now, why this figure is important? Let me go back to few slides back. Okay, look at this figure. Here, this is gate, this is oxide, and this oxide has got the permittivity or the dielectric constant K is equal to nearly 4. This is 4. What is meant by dielectric constant? Dielectric constant epsilon r is the permittivity, which actually tells us what is the capability of this material to store the charge. The capability. More the amount of epsilon r, more the capability of this material to store the charge. Okay. Therefore, if you may remember, in the parallel plate capacitors and all, the capacitance value is given by epsilon A by D, where epsilon is the epsilon 0 into epsilon R, and tantalum caps and different mica caps and air caps and many more, paper caps. Every dielectric material has got its own different value of epsilon R, and therefore capacitance means the capability to store charge, it will vary. What happened since 40 years, since the invention of MOSFET and manufacturing of the chips and all, SiO2 material, silicon oxide material, it is well matured and very much popular. We used to use SiO2 material having epsilon R is equal to 4. Here, SiO2, it was doing well. Everything was going well. No problem. Because this channel length, I will again go back to back figure to make it again, to make you understand. Okay. This channel length was higher. But when channel length is shrinking down, when device is becoming smaller and smaller, say typically this problem started arising beyond 4 nanometer. When the channel length L is becoming less than 4 nanometer, the problem started being faced now is about the oxide layer. So you need here the thinner and thinner oxide here to have control over the current. See, what is the purpose of MOSFET? That we should have the gate voltage should have enough control on the drain current. And that is possible with small channel length when you make the oxide thickness smaller and smaller. When oxide thickness became smaller and smaller, what happened that it is becoming a very small thin film. In those thin film, hardly maybe the 4 layers of atoms of SiO2, molecules of SiO2 were capable to reside. And when something becomes very thin, just remember what happened say 100 years back, that the tunneling mechanism or the quantum theory came in the science in maybe 1910 or 1915, 1920. in those days. When something becomes very thin here, then the electron starts behaving in a very surprising way. Mr. J.J. Thomson has proved in 1897 that the electron is a particle. But maybe after 10 years after that, his son himself proved that the electron behaves like a wave also. Therefore, electron can behave as a particle, as a wave by both the ways. And when oxide thickness layer POX becomes very, very small, because of the tunneling effect, because of quantum effect, that electron start penetrating from this gate supply voltage into the channel immediately. This is called as leakage, and this leakage started happening when channel length becomes smaller and smaller. This is the problem, and because of the problem here, we all are involved in the today's presentation here. What are the new devices because of this problem? I think I addressed to the meaning of POX, the meaning of Epson R, because of what there is need of invention of new devices and how new devices have become very popular. So coming back to our parameters once again. So keep in mind that silicon dioxide was very good, but having Epson R is equal to 4, and thickness, very small thickness is not possible. Therefore, we are going for the new device, new dielectric or high K dielectric material instead of SiO2, instead of silicon dioxide. Yeah, okay. One more term here, again very important, called as velocity of electron. Everybody knows velocity of light and velocity of electron. They both are same in free space and no difference. But the moment electron are moving in some metal or in semiconductor, the speed is not equal to speed of light. It will vary. And in channel or in conductor, the velocity of electron is given by is equal to mu into E, where mu is the mobility of electron and E is the electric field applied to that device. Correct. Now, electric field, just now we have seen electric field means it is how much voltage is applied to the device per unit length. Higher the amount of electric field, there will be higher force on the electron. Therefore, the velocity can increase. If you want to increase velocity, you can increase the electric field, no doubt. But there is certain physical limitation. Beyond certain value of electric field, the velocity of the electron cannot be increased. That is called as velocity saturation. And there is no use of increasing the electric field beyond that. Okay, then there is other way that how to increase the velocity of electron by changing the mobility. Okay, now mobility of electron also will vary. It will vary because of the packaging, because of technology, because of the material. There are many parameters which are deciding the mobility of the electron. Let me tell you just in short what is meant by mobility. It is actually ability of the electron to respond to electric field and to move faster. Just like imagine you are driving a car, you are driving a truck. Imagine driving a truck on highway, and there is a traffic on highway, enough traffic. Therefore, your velocity, speed definitely is less because of more and more constraints in the path. But if you are driving a two-wheeler, a bike on highway with the same traffic density, you can find out your path very easily. That means this is the indication that the bike has more better value of mobility as compared to a loaded big truck. Therefore, bike can attain better velocity, better drift velocity, final drift velocity as compared to truck on highway with the same traffic conditions. This is the meaning of mobility. Therefore, new devices are invented based on this term also, that how to increase the mobility. There is HEMT, high electron mobility transistor. HEMT is a very famous transistor used in deep space, in the space shuttles, in advanced electronics, in pacemakers, who will go to that as a device. Therefore, in this way, this mobility plays important role. Okay, the conclusion from this slide is the mobility is the one term on which the focus is there. Dielectric constant is the second term. Dielectric constant of SiO2 material, for silicon material also. Energy band gap is again very important term. If you change the material, energy band gap will change. Remaining three are no doubt the physical constants. Okay, based on this, now we will move ahead to few again fundamentals, which we will touch and go ahead. Whenever there is electric field, there is voltage. Mathematically, gradient, it is a mathematical term. The gradient of scalar potential voltage is nothing but the electric field in volt per meter. Just keep in mind, forget the equipotential figures and all, but voltage gives the electric field simply proportional. Next is whenever there is a voltage, gradient of voltage is electric field and there is electromagnetic vector potential available there. Okay, we'll not focus on the electromagnetic spectrum here. The Poisson's equation says that with the constraints on the boundary conditions available here, Poisson's equation shows that del square V is equal to 0. Just keeping in mind, I'm just making you aware. And then before moving to the next device, the first device, new device of VLSI, we'll just quickly go through the Faraday, Maxwell, Ampere, Kelvin, and Stokes equations, which normally as a schoolboy or the college student, ENTC or students normally are very much afraid of these equations, but very fantastic, beautiful equations after Einstein's equation. These are the equations given by Mr. Maxwell. Nobody could do anything after that, really, in the unification theory, integral and differential, in which I will just give you simple example here. This is the curl of E. Curl of electric field is nothing but d by minus d by dt of B. B is the magnetic flux density, and B is nothing but mu into H. H is the electric magnetic field intensity. It shows that whenever there is electric field, there is a magnetic field. Similarly, this shows that whenever there is magnetic field, there is electric field, and vice versa. This is the unification of the theory that magnetic and electric fields are conjugate of each other, and when one exists, second always by default exists there. Keep this thing, do not go for the meaning and recalling all equations again, but only summary of this single slide is magnetic and electric fields are, they always exist, they have the coexistence. When one is there, other is must, or it always exists. Okay, all right. It's all about the fundamental MOSFET, which we are using since 40 years. It is quite mature technology. And why we want to go for the new device? There are many reasons. Because of channel shrinking, more amount of leakages are there, speed is not increasing, more power dissipation. There is need to go for different materials to change the mobility, to change the Epson R value, to change the resistivity, to change the capacitive effects, to reduce the substrate coupling, and many more. The first device is the graphene FET. Graphene FET is now coming in the market, and very soon it will definitely enter into the market. Graphene is the carbon material. This is the film of graphic hexagonal lattice structure. This is the structure of the molecule of the graphene material or carbon material. This material has got this property. This property is called as Dirac point of graphene structure. Dirac is the name of Paul Dirac, who was a very good scientist, very famous scientist, Paul Dirac, or Dirac function, Fermi Dirac probability function. Many of you must have heard these words also. This is bulb to gate voltage, body to gate voltage, and this is drain current. If we manufacture MOSFET with the graphene as a material, as a channel, then it has got this property that when the gate voltage is positive, then the flow of current will be because of electron, and when the voltage is negative, it is because of hole. And when there is no voltage, when there is no gate voltage, that time the device ideally does not carry any current and forget leakage current, and that time device is called as off device. This is the typical property of this graphene material, thin film material, which is used in the graphene FET, graphene field effect transistor. Like a MOSFET, it is a graphene MOSFET now. This is the, in general, the theory mentioned here, what just now we discussed. In purposely, I will read out few texts so that you can have the linkage of oral talk and the text available here. Graphene FET uses a single layer of carbon atoms, graphene, as a conductive channel. It has advantage of ambipolar nature and very high carrier mobility. Again, the term very high carrier mobility. Just now we talked about the mobility, and if we learn when mobility is more, the velocity of the electron definitely is more, and we can get the device with high speed. Substrate. What these are the content of the device. Device has got substrate, channel, source, drain terminals, gate, and dielectric layer. Substrate is a silicon wafer with thin insulating layer of SiO2. Channel is made up of graphene onto SiO2 layer. This serves as active region where charge carriers flow. Source drain, no doubt, are metal contact, aluminum or gold or depends. Gate is again a back gate, silicon substrate itself, and dielectric layer, the top gate version, thin insulating film separates the gate from graphene to prevent the current leakage while allowing the electric current or field modulation. It looks like this. This is structure of graphene FET. This is source, this is drain, and is SiO2 material, on which this yellow is the graphene channel, graphene material channel. The same thing is mentioned here. Since it is a very thin layer, this thin layer lattice structure is mentioned here. This lattice structure has got the property that when gate voltage is 0, device is off. When gate voltage is positive and negative, accordingly, there can be flow of electron and hole, and the device can be on. This is the operating principle of this device, graphene FET. We shall call it as a GFET. It operates based on the field effect, where external electric field form gate modules the density of charge carriers in the channel. The Dirac point, as what we discussed, the most distinct function of graphene is its ambipolar behavior. Its natural state, graphene's conduction and valence bands meet at a single point called as Dirac point. At this point, the current density is at its minimum and resistance is at its maximum, means as like as device is off. But when we apply the voltage to gate, the Fermi level of graphene can be shifted, and positive gate voltage shifts Fermi level into conduction band, attracting electrons to the channel, and negative will give further conduction because of holes. In this way, there is no band gap. No band gap is again advantage of graphene FET. See, in the previous slides we discussed that band gap for silicon is say 1.1 electron volt. In case of graphene, this problem is nullified. If there is a band gap, the electron definitely travels from first point to second point because of thermionic emission. Thermionic emission means when the device is applied electric field, then electron gets electric energy and it can move from one point to other. And the electric field is to be maintained constant so that the current can achieve its drift attained velocity. This problem is not there in this graphene FET, and because of that, this device does not have, or it has very, very low power dissipation, and it can achieve very high speed. Because of very high speed, this is symbol for GFET, because of its very high speed. Then this is very popular application of GFET is called a distributed amplifier. Distributed amplifier means cascaded amplifier. Distributed amplifiers are very famous to have very high bandwidth amplifier. To have high bandwidth, distributed amplifier is the key circuit or the idea. Therefore, this is a graphene device, one graphene transistor FET, one T1, T2, T3, T4, they are in cascade. Input signal is applied just like a common source amplifier. Nothing like that only. There is a DC supply voltage given here called as a drain bias, and there is output available here. It is just typical circuit diagram. I am showing it here to make you aware that what is the utility or uses of graphene FET. So this is very famous no band gap problem. These are the applications of GFET. I will quickly read it out. Biosensors and chemical sensors. Since every atom in the graphene channel is on the surface, the device is incredibly sensitive to external molecules. Therefore, graphene FETs can detect DNA, proteins, or glucose levels at extremely low concentrations. Since there is a thin film of graphene available, it can be very sensitive to physical parameters. In high frequency, graphene has got ultra high frequency, ultra high electron mobility, and GFETs are used in RF applications such as mixers and amplifiers that operate in the gigahertz range. Flexible electronics. uh, Wait for 10 seconds. Okay,
Sorry,
I'm
you're on
resuming
mute.
back. Sir, am I? Yeah,
Yeah,
sir, am I
now
audible?
you are. Now you are.
Okay.
Yes.
Yeah. Okay. Okay.
Uh,
Now,
you can start with HF. We heard about biosensors and chemical sensors.
yeah. Okay, I'm going to that.
Ah,
The moment GFET, graphene FET, it is thin film kind of thing. It is very much sensitive to the as a sensor. Because of high mobility, it has a high speed, therefore applicable for HF and RF applications. Purposely mentioned here as a mixer, amplifiers operate in gigahertz range. It is very famous in flexible electronics, where graphene is mechanically strong but flexible. Therefore, it can be fabricated on the plastic on variable substrate so that the clothing can become very smart, and along with it is a smart clothing, intelligent clothing on which the sensors can be deposited. And no doubt, photo detectors. These all are the advantages of graphene device, uh, which is very with a very high speed and all. Fine. In this way, this is I will just quickly uh, see what we have seen. This is GFET, its operating principle, the terminals and the content of the device, structure of device, operating principle of the device. Typical example of RF amplifier, wideband amplifier by using GFET. Then applications of GFET, as we have seen, it is commercially being used now. Now the next device. It is molybdenum disulfide. Instead of calling as a chemical name, we'll call it as MOS2, not MOS. Not MOS. MOS is the metal oxide semiconductor. That is a different thing. MOS means MO is for molybdenum and S2 is for disulfide. And it is memristor. Memristor is a general literature name given to this device, but actually it is MOS2. Okay, but hereafter in the presentation and later on also we'll call it as a memristor because it is a register with memory. It's got memory capability. MOSFET does not have the memory capability as a device, but this device has got the memory capability also. So let us go for this device. It's again becoming very famous in case of uh, bulk memories. Nowadays laptops and all are coming with the SSDs, the chip memories, not the hard drives, not hard disks now. So those all memory chips can be very short, very shortly will be replaced by the memory store. Okay, what is the meaning of this? Purposely, I will read it out so that you will have the continuity. Next generation non-volatile memory device that uses atomically thin layer of MOS2 as a switching medium. It remembers its previous resistance state based on the history of the voltage applied to it. How it happens, we'll come to. It is a MIM, metal insulator metal kind of structure. Okay. It has got active layers, electrodes, and substrate. Active layer, these all are the now chemical things. A thin film of ranging from monolayer to several layers, no doubt, MOS2, is a transition metal dichlorogenicide, TMD, that offers high thermal stability and an atomic scale footprint. Okay, it is just about the chemical composition. Electrodes are no doubt. Again, the source, there is a drain. The material like gold and all used for the electrodes, active diffusive electrodes, materials like silver, copper, or aluminum, they are used depending upon what kind of conductivity or ion migration we want or we do not want. And the substrate, it is typically a wafer or flexible polymer for variable applications. Its structure is a okay, we'll go to structure, uh, or before that, yeah, okay. It's operating principle. The core principle is resistive switching. The device toggles between high resistance and low resistance state through the movement of ions or vacancies. High resistance is called as HRS, low resistance is called as LRS. So how there are two ways to operate the device, memory store. One is filamentary mechanism, which is very famous, and second is non-filamentary. In which, what is meant by set and what is meant by reset? When the positive voltage is applied, metal ions sub vacancies within the MOS2, that is migrate and align to form conductive bridge or filament. When we applied gate voltage, it forms a filament. This bridge connects the two terminals or electrodes, dropping the resistance significantly. It's called as LRS. Means the meaning of this is when we apply gate voltage, the filament or thin layer is formed and device is on. It offers low resistance. Look at reset process. Applying reverse voltage causes the filament to rupture or dissolve, and that film will go out, returning to the device to insulating state, means high resistance state. It means when we apply, say for example, when we apply positive voltage, device will offer, the channel will offer from drain to source, channel will offer low resistance, and when the voltage on the gate is negative, the channel will offer high resistance. It means the device will be on here and device will be off here. This is the meaning of that. The fundamental concept remains same. We want that the gate voltage should have control over the channel current. It may be any device, it may be FinFET, it may be this graphene or any. Everywhere we want this only, that it should behave like a low resistance and high resistance. So this is the property of this device, and this is structure. It is a chemical kind of structure mentioned here. This is a high resistance state and this is low resistance state. It is mentioned, it is positive when we have, it is a more amount of density of electron available here. Therefore, conductivity is more. Since conductivity is more for the channel offers low resistance. Because of less number of electrons, the conductivity is less, and therefore it will offer high resistance. In this way, the device can behave like on and off. The very important thing is mentioned here. The accumulation of charge carriers or defects at the boundary charges changes the ease with which electron can tunnel to allowing the more gradual or analog like change in the resistance. You may say that there is low resistance and high resistance. In between, is it possible? So in between also it is possible if we apply the gate voltage accordingly. But this is very popularly used as a switch in digital way than analog. So this is again few figures which will make you again slightly more aware. This is try to make you aware that how the foils are there, how the films are there. The dimensions are mentioned here, 0.7 nanometer, because of what tunneling effect can start. Tunneling, let us revise back. Tunneling effect is the movement of electron when electron enters from one side to other side. This is the quantum theory principle, and in which the behavior of electron, sometimes behaving like a particle, sometimes behaving like a wave. The advantage of this behavior of electron is taken care in this tunnel. Whenever you hear the word called as tunnel or high mobility, specifically tunnel, always keep in mind that dimensions are very small, and if the ability of electron behaving as a particle or as a wave is taken as advantage in the tunneling effect. This is the things mentioned here, a reset and set, no doubt, high resistance and low resistance, LRS, HRS. Look at here, the gate voltage values are mentioned here, but the currents are here in milliampere, here current is in microampere. This shows high resistance. This shows the device offering low resistance. This again shown here. It is high resistance value. This is low resistance value. High resistance value is 10 raised to 8 ohm, 10 raised to 10 ohm is giga ohm. Low resistance values are in the range of 100 or below 100 ohm. This is the area in micrometer square. So this is all about this device. Purposely, I tried to mention here the features, typical numerical values, electrical parameters. Low switching voltage, it is below 1 volt. On-off ratio, on to off ratio of the current is 10 raised to 4. It means when device is off and if the device is on, then on current divided by off current, this ratio is 10 raised to 4. 10 raised to 4 means 10,000. Means on current is 10,000 times more than the off current. Quite good value. It's good value. Fast switching speed, no doubt, in less than nanosecond. And good endurance. It is by mistake. It is by mistake. I made here 104. It's not 104. It is 10 raised to 4. 10 raised to 4 cycles. Good endurance 10 raised to 4 cycles means 10 raised to 4 times it can be switched on and off without any damage and without affecting the performance. That is normally we call in design called as MTBF, mean time before failure, or giving the performance without any variation, any violation. That is called as in industry. This term is very famous, called as endurance. And in case of VLSI industry, it is very famous to mention the endurance. If you go for any FPGA, for example, you open the manual of Xilinx or any AMD now, it's taken over AMD. Then if you look at the FPGA, in the data sheet, you will find this kind of term called as endurance. Then how many endurance cycles? 10,000, 20,000, 30,000 endurance cycles means how many cycles that device can be utilized again and again without change in the performance parameter. It's all about features. Fine. These are the applications of this device called as memory stir. Since the gate voltage we apply and the film is formed, and if gate voltage is removed, then film remains as it is. That means it behaves like a memory. It can behave like a memory. That is very important thing. Therefore, neuromorphic computing, it is used for artificial kind of computing purpose. Significant memory stir can mimic biological applications, and in ANN it is used. Non-volatile random access memory. It is very funny word, random access memory. When we talk about RAM, now normally RAM is volatile, but we can make a non-volatile RAM because of this memory stir. It is very good advantage or utility of this device. In memory computing, high performance computing, the memory on chip is being manufactured now with the help of this memory stir. And it is very useful in von Neumann bottleneck. The audience, among the audience, if somebody is there about the computer architecture and all, he must be aware of what is by von Neumann bottleneck. Normally, when the processor design takes place, normally the computing engine works is von Neumann, very typical type of architecture called as von Neumann, where the bottleneck is formed because the instructions are executed one by one. And to accelerate that instruction execution, people added pipelines, different pipelines, and adding DRAM, adding the cache RAM, cache memory on the processor. These many things people are doing to increase the speed of the processor and to remove the bottleneck because of von Neumann architecture. So this memory stir, if we make the memory because of this memory stir, the high density of the memory can be formed to make a cache memory, and this bottleneck can be reduced and the processing can be again faster. And therefore, once again, because of this tiny sizes, miniaturization, it is again flexible, very famous in flexible and variable electronics, smart skins, smart kind of wafers, fine kind of fabrics. It is possible. So these are the applications. In this way, let us again go back to have the continuity recap that memory stir has got the capability to behave like a memory. It is a device. It is operating principle that the film is created and film can be destroyed. If not destroyed, it will remain there like a non-volatile memory. Therefore, it behaves like a MOSFET along with the memory. It is a very good advantage. Then structure we have seen, operating principle we have just touched to it. few features we have seen, applications we have seen. Okay, let us move to the next device called as FinFET. Many of you might have heard this name. It is quite mature now. Uh, in the audience, if the audience number is say 1,000 currently, just imagine there are 1,000 audience available here. 1,000 audience have got 1,000 cell phones and 1,000 laptops. Remember, your every cell phone has got now the processor made up of this device called as FinFET. FinFET is very mature now and available now in the processors for low power dissipation, for high speed, and very famous in case of all the cell phones. What is meant by FinFET? Fin is the typical name. The shark fish has got the fin. That fin is a literature word used to the field effect transistor. It is nothing but the literature word attached with the FET. A FinFET is a non-planar, three-dimensional transistor. Remember, MOSFET was two-dimensional planar structure. FinFET is a 3D structure that replaced traditional flat planar MOSFET to allow the semiconductor industry to scale below 22 nanometer node. Its 3D design effectively suppresses leakage current, which is the primary hurdle in case of modern chip manufacturing or in miniaturization. What is construction? Substrate, fin, gate, dielectric. Since lot many slides are there, I will not read out every word. Substrate is made up of a silicon wafer or SOI. Fin. This fin is a thin wall, vertical silicon wall that is between the source and the drain. And gate is like a gate normally, but it is on three-dimensional gate, three sides. It's a tri-gate. And the gate dielectric is a high K material, HFO2 called as hafnium oxide. HFO2 has got a good amount of epsilon R permittivity. The permittivity of SiO2 is 4. It is just 4. But the permittivity of HFO2 is approximately 25. 25 is a big value. It is called as a high dielectric material. It has got a good capability to store the electric charge. And therefore, this dielectric is really useful, very good and useful in making this FinFET. This is structure of FinFET. This is substrate. This yellow is a source. On that side, that is a drain. No doubt, in between there is a channel made up of silicon, no doubt. But this blue on three walls. First side, this side, top side, and that side. On all three sides of the channel, there is a gate. Therefore, gate is gate 1, gate 2, gate 3. Therefore, it is a tri-gate kind of thing. Why this structure is made? Because if we have gate surrounded, the whole channel is surrounded by the gate on three sides, not four, on three sides, then the control on the drain current can be easily obtained. Anyway, why we go for invention of new device? Our aim is in simple way. Our outcome should be the drain current, the drain to source current should be well controlled because of gate voltage. And that gate voltage can acquire good control over the channel, over the drain current in this way instead of MOSFET. Look at the MOSFET. In MOSFET, I think I have the figure. Okay, not compared here. Okay. In case of MOSFET, the channel is controlled by the gate only on one side. Remaining three sides are not controlled. Therefore, control is not that much supreme. Here, the control in case of FinFET, because of this fin shape, the name is given fin, like a shark fish fin. The control on the channel current is well acquired because of this three-dimensional gate. Its microscopic photograph is mentioned here. These are the fins, and we can make the first MOSFET, second MOSFET, third MOSFET. By adding the fins in parallel, we can have the multiple MOSFETs. I mean to say FinFETs in parallel, and we can increase the current capability of the FinFET very easily to make it operative at high current possible. Then its operation principle, it is automatic control, no doubt. Instead of reading everything, I will just a nutshell, I will tell you. The multi-gate control, fully depleted channel, and with quantization. In case of multi-gate control, it is in planar MOSFET, the gate only control the channel from the top. But as a transistor shrink, the drain's electric field start to leak and current through the bottom of the channel. In FinFET, these leakages are not there. Therefore, the device can be really truly off. Similarly, there is no penetration, there is no leakage current, depletion. Therefore, FinFETs are definitely very good. And at the end, the FinFET transistor width is no longer continuous. To increase current capacity, we can have the multiple fins in parallel. Therefore, current capacity can be increased. Therefore, size of FinFET, remember, size of FinFET is definitely less than the MOSFET, its counterpart, number one. Second, the FinFET has got very less amount of leakages. And third, very less amount of capacitances with the FinFET. Hence, it can operate with high speed. Therefore, its applications are now mobile SoC, system on chip, your cell phone. Every modern smartphone processor utilizes FinFETs for their balance of high speed and low battery drain. You can just recall the earlier devices, earlier mobiles. When FinFETs were not there, not commercially used, and the processors and the whole cell phone was made up of the MOSFETs. Therefore, MOSFET has got the leakages definitely more. And when though you use the MOSFET or though you do not use, though you use the cell phone or do not use, once it is on, the battery drain is there, and the life of the battery reduces down when you use the cell phone for longer period. After 2 years, 3 years, 4 years, the battery used to drain out very quickly, really very quickly. And that problem is now addressed and reduced down to really effectively because of the FinFET. The cell phones are made up of FinFETs. The battery drain is not a big problem at this moment. But no doubt there are more amount of apps, there are more graphical usage which needs more amount of power. Therefore, battery drain is there. But that battery drain is there not because of the device, it is because of the fantastic and advanced applications or apps. Second is high performance computing. No doubt when we go for the uh, supercomputers, high performance computing, HPCU, Intel's Core, AMD's Zen, GPUs, NVIDIA is very famous. You must have come across NVIDIA is very famous in GPUs, graphical processing units. The FinFETs are very good and very good candidate for them to manufacture their processors in the gigahertz range, more than gigahertz range, and without melting, means without giving rise to power dissipation. The artificial intelligence accelerators are very famous in case of FPGAs. You go for AMD's Xilinx, you will find the array of FPGAs uh, which are very famous inbuilt, called as AI accelerators, DSPs, and signal processing accelerators. These accelerators are built with the help of FinFETs because of high density, because of low leakages. And no doubt about SRAM and cache. The high speed static random access memory, SRAM, and cache memories on processor can be manufactured, and FinFETs are very good candidates for them. These are typical specifications of FinFET. This I have taken from TSMC, Taiwan Semiconductor Manufacturing Corporation. Taiwan is very famous, TSMC. Those who are among the audience, if somebody is involved in manufacturing the chip fabrication, then TSMC is a very good solution for them. TSMC, no doubt. Intel, MOSIS is there, no doubt. Samsung, good players in the fabrication. No doubt, Tata is there now in India. We have started our fabrication. Majority of the industries are in Gujarat, and Tata is the main vendor, main contributor into that. All right. These are the specifications of 7 nanometer node. While reading this, keep in mind what was there in MOSFET. Operating voltage, see here, it is 0.7 to 0.8. Gate pitch is hardly 56 nanometer, and fin width is hardly 6 to 7 nanometer. Fin height is no doubt. Height is more than the width, therefore it is called as fin, like a fish fin. Threshold swing. Threshold swing is 68 millivolt per decade. Sub-threshold swing means, let me define it. Sub-threshold swing means it is the amount of gate voltage giving change in the drain current 10 times. Look at here. Sub-threshold swing means When the gate voltage changes by 68 millivolt, the drain current changes 10 times. And when sub threshold means when gate voltage is less than the value of Vt, means when device is off. When device is off, then that time gate current should be zero, but some leakage current always is there. Then what amount of, by what way the gate current is, the drain current is changing? It is changing by this way. It is a typical mathematical term. Ideal value of this term is equal to zero. Means sub threshold swing should be 0 millivolt per decade. In case of MOSFET, this value is 50, 60 millivolt per decade. In case of FinFET and the advanced devices, this value is still smaller and smaller. Smaller the amount of this value, better is the kind of device, better is the amount of leakage, means small is the amount of leakage, and device is called as good off device. Threshold voltage is hardly 0.2, 0.5 volt, and transistor density is 60 to 100 millions of transistor per millimeter square. All right, therefore it is very much famous because of high density for cell phones. We shall go for the quick recap of FinFET. FinFET, because of the fin structure, this is the fin. Keep in mind, the channel is surrounded on three sides from the, because of the gate. Therefore, good control on the drain current is achieved. Very famous operating principle. It behaves like on and off very faster. Applications are in SoCs, in cell phones, high performance computing, supercomputing, AI accelerators, FPGAs, everywhere, and the memories. Quite mature now, FinFET. Few years back, FinFET was the dream, and now FinFET has come into reality, and we are using it. Our cell phone and laptops have got now the FinFETs. Okay. The next is the derivative of FinFET. We remember that in FinFET, the gate, the channel is surrounded on 3 dimensions. Because of the manufacturing limitations in the fabrication labs, people surrounded the channel on 3 sides. Then again, the people, and the invention has no end. Innovation has no end. Development, R&D has no end. And the people thought of why not to surround the channel on 4 sides. Then the concept came, and the fabrication lab got developed, and that new FET is called as a GAA FET, gate all around. That this FET has got the gate surrounded on the channel on all 4 sides. I will purposely I will read out few sentences to have the continuity between the oral and the text content. It is the next major evolution transistor architecture succeeding the FinFET. It surrounds on all 4 sides. The channel is again silicon nanosheet, nanowires. The gate is a typical gate. It is a wrapping on all 4 dimensions sides. Gate dielectric is HFO2. I told you the HFO2 material has got a very good epsilon R relative permittivity. That means it is high K material. High K material gives drastic reduction in the leakage current, and therefore the size of the device can go really very low, very small. Source and drain are the nanosheets, and inner spacers are used here. This structure construction physical of GAA FET. This is structure. Look at this is FinFET and this is GAA FET. FinFET, the channel is surrounded on 3 sides, but in gate all around, channel is surrounded on all 4 sides of the channel. Therefore, this is the first channel, this is the second channel. There is no limit. You can add the one more channel. When you increase number of channels and the gate is surrounding every channel, you can have the increase in the current. You can go for, you can build a power GAFET who can control, which can be used for high power applications, high current applications, which with good control over the drain current. This microscopic photograph is mentioned here. The first channel, the second channel, third channel. This cross section is shown here. And look at here, it is surrounded by the gate. Since channel is surrounded by the gate, the perfect control on the drain current can be obtained. That is the key point of GAA FET. It is operating principle. It has a superior efficiency. It has the maximum electrostatic control. Therefore, short channel effect is not there. Deep the steep subthreshold slope. This subthreshold slope is now more than, its value is smaller than 60 millivolt per decade, as we discussed in earlier slide. And with customization, we can put them in parallel. If we put them in parallel, we can really build a device with good current capability, or the power device. Its applications: 3 nanometer and 2 nanometer logic, TSMC and Intel, Samsung, they already are using it. In AI, in case of AI, it is very much famous in case of the accelerators or thermo isotopic generators in case of devices. In AI, TPUs, NPUs, natural processing unit, data centers, they use this device for applications. Next generation mobile devices. GAF, it is slowly entering into cell phone. If they enter into cell phone and commercialize mature technology, again the battery drain problem will be solved, will be very much nullified. And no doubt supercomputing, because we need to tackle the heat dissipation. Therefore, we need the device in which the leakages are less, therefore heat dissipation will go low. These are the typical specifications of this device. Operating voltage, it is this range, 0.65 to 0.75, sheet width, thickness, pitch. This is 15 to 30% better than the FinFET. No doubt, it's derivative of FinFET, but far better than the FinFET now. Reduction on the power. As compared to FET, it is 50% better in the power saving. And sub-threshold swing is again good value, 65 millivolt per decade. That means very low amount of leakages. I will go again for a recap for GAA FET. G, gate all around FET, is a derivative of FinFET. The channel is surrounded by the gate. Good control over the drain current, therefore good control over on leakages. This slope is again reduced down, very famous in the computing application, because we want a high dense memory with low power dissipation with minimum drain of the battery. Specifications typically we have seen here, and we try to compare here with respect to FinFET, so that we can understand what is the capability, why GAA is better than, or GAA FET is better than the FinFET. All right. And now the next device is the tunnel FET. There is no end. In FinFET, in GAFET, tunneling principles are not there. In earlier mathematical slide, we discussed that since electron can behave like a particle as well as a wave, why not to use it, take its benefit in commercial way? If we go by the tunneling principle, quantum principle of electron, the principle is when there is a thin layer of some material, and if electron charge is applied to the material, electric field is applied to the material, the electron can penetrate, though the resistance of the material is very high. Though resistance is very high, though electric field is very low, though the current should not flow, but still electron can go there from one side to other side by the principle of duality, number one, quantum mechanism, and second, tunneling effect, and third, the property of electron behaving like a particle as well as the wave also. This phenomena is taken care as advantage to build a new device. Therefore, it is just mentioned here. It is experimental transistor designed specifically for ultra low power electronics, quantum mechanical tunneling. Its construction has got PIN kind of structure, pin diode. Those who are concerned with the microwave has got a gun diode and then the pin diode in case of gigahertz, X band, S band, Q band, C band ranges. Those people must be aware of what is by pin. Pin means P type, intrinsic, and N type. This kind of structure is there, very thin structure. Therefore, there is a source, there is a drain, there is a channel, but channel is intrinsic now. In MOSFET, channel is not intrinsic, it is doped material. Here, channel is intrinsic to have the tunneling effect. Then gate, no doubt HFO2 because of high K material, and remaining are again the compounds, class 3, class 4 compounds of indium arsenide and gallium arsenide. operating principle is, it is band-to-band tunneling. Off-state means when there is no gate voltage, energy bands of source and channel are misaligned. When energy bands are aligned, then electrons cannot penetrate from one side to other side. On-state means when both energy bands from source to drain, when they are aligned, then electrons can enter from source to drain very quickly. It's called as tunneling effect. Those who remember tunnel diode is quite old, maybe 50, 60 years back. People use tunnel diode in communication, RF applications, but the principle is same. In the tunneling effect, this pulling down of the electron is possible. And remember, here the mechanism is not because of the thermionic emission. In MOSFET, because electrons are made hot because of electric field. Because of that, they will move or they will travel from source to drain. But in case of uh, this device, tunnel FET, instead of making electron hot, electron is forced to move from source to drain by making the energy band levels equal. That is tunneling effect. Therefore, it's called as cold carrier. Remember, field effect transistors, MOSFETs, FinFET, GAAFETs, these all, whatever, graphene, those all were about the hot electrons, but this device talks about cold carrier. Therefore, since hot electrons are not there, there is no jumping and only tunneling effect from one side to other, this device remains cool. And since the device remains cool, it is very good for high density device fabrication as shown it here. This is MOSFET. This is gate. For MOSFET, it is a source, drain, and gate. And this is tunnel FET. There is a gate. This is source. This is drain. And in between is intrinsic material. Because of the thin film, because of application of positive gate voltage, the energy bands are so aligned between first and second, are such aligned that electrons will move from this P side to N side without making them hot. Therefore, there is no hot electron effect, there is no short channel effect, and the device can switch very quickly without any power dissipation. Ideally, dissipation is zero, practically very, very less as compared to MOSFET. This shows the sub-threshold slopes. See, in case of MOSFET, this is very sluggish. Very slowly it will go here, sub-threshold. In case of tunnel FET, it goes very quickly. Therefore, this ratio, how many millivolt per decade? This ratio is smaller than 60. In case of MOSFET, it is 60 millivolt per decade or more than that. Therefore, sub-threshold swing or sub-threshold slope of the device is better here as compared to MOSFET, as compared to FinFET also. Its applications are everywhere. When there is energy kind of saving in IoTs, in wireless sensor networks and all IoTs, because of the low power dissipation kind of thing, we prefer for the medical implants, variable electronics, space electronics. This is the very big advantage. Please concentrate on this medical implants. In case of pacemakers, pacemaker is sitting on the heart and taking care of AV node, SA node, and giving the pulses uh, to the heart. And it is once the surgery is done, the pacemaker is fit there. It is expected that for at least 10 years, pacemaker's battery will not drain. And therefore, the pacemaker's ICs used in the pacemaker should be very carefully designed, low frequency ICs, but very, very low power dissipation. This kind of device, tunnel field effect transistors, are very much useful in case of these pacemakers, where speed is not important, but the leakage or the power drain is very important, because we cannot operate the patient very frequently. When there is threat to life and power drain, this is a very good candidate, this device. And in space electronics, in deeper space probes, when the space shuttle goes away from the sun, the solar panels are of really no use, because the amount of sunlight falling on the solar panel cannot give that much energy, or the storage amount of energy is not there. That time the different uranium is used there. When the uranium atoms decay down, they release some energy, and that kind of energy is used, and that energy is used for devices, ICs to operate. Therefore, this kind of tunnel FETs, if ICs are made up of this, of very low power dissipation, this kind of devices are very useful in case of deep space probe applications, space as well as medical implants. These are its typical specifications. Look at here, VDD 0.2 to 0.5 volt. This is sub threshold. It's quite good value, less than the 60. On off current, it is very off current is C. It is how much? Less than 1 pico ampere per micrometer, and ranging to femtoampere, 1 femtoampere per micron. On current is ratio is again, this is mistake. It is 10 to 5 to 10 to 7. It's a good amount. 10 to 7 means how much? It is a 10 million. That means on current, on off current is 10 million times less than the on current. It is good device. And threshold voltage is a 0.1, 0.3. Therefore, it is a good candidate for uh, low power dissipation. I will let's go for a recap of this tunnel FET. Operating principle is a tunneling. Principles are that energy band are aligned, the tunnel is formed, and electron can move quickly as a cold particles. Therefore, this TFET is superior to MOSFET and superior to FinFET also. Its applications prominently in medical and the space probes. Most important here is the ratio of on to off current is at least 10 million. Fine. One more device. Actually, 2-3 devices are planned there, but I will, since time doesn't permit, quickly I will go to this device, and remaining PPTs will be available with the coordinator, no doubt, Parikar sir also and Doshi madam also. Therefore, you can have that PPT PDF from them, and personally you can go through that. High electron mobility. Again, recall at the start of the presentation, we were talking about mobility. If the mobility of the particle is made more, the device can be made more faster. This device is talking about the mobility only. Therefore, since time is less, I will not read out the chemical composition. I will just explore you how the device is made on and off. This is source, drain, and gate. Multiple chemical layers are kept in between, and by adjusting the Fermi level, you know, the Fermi level is the average of conduction valence band. If we align the Fermi level from source to drain, the electron can easily penetrate from this side to this side. That is a Fermi level, typical Fermi-Dirac probability function. Accordingly, this device will switch on and off. Its applications are in telecommunications, in base stations, satellite communication, radar communication, satellite receivers. In case of LNBs, low noise block, on you must be having your cable TV antenna, parabolic reflector antenna on your apartment's terrace. In just in front of parabolic reflector, there is LNB, the low noise block, which is a low noise. That block consists of very high bandwidth low noise amplifiers, LNAs, and those LNAs are made up of gallium arsenide HEMT, high electron mobility transistors. These transistors are very good to pick up the weak signal from noise from the space. Radio astronomy, power electronics also, the device is very, very famous. Typical specification, look at the first term is very important. Operating frequency is beyond 100 gigahertz. This is the most important term. And the last, the noise figure is less than 1 dB. Because of these two things, first and last, this device is becoming very famous in case of RF applications. Spintronic device, I will skip it because of less amount of time is available with us now. It is a purposely I am showing you one just to give make you aware of what is meant by low noise amplifier. The device M1 devices M1 and M2 are associated with different inductors and caps and all. This is the way how the RF amplifier is designed and manufactured. Therefore, if M1 and M2 is made up of FinFET, if they are graphene devices, if they are HEMTs, high electron mobility transistors, then definitely the LNA can have really very low noise, very low amount of noise figure, good amount of noise figure, and will have very high amount of bandwidth also. This is the micro photograph of LNA without electrostatic discharge or with ESD mentioned here. These L's are indicating here the inductors. And remaining these, no doubt, these black are mentioned here, the MOSFETs. The MOSFETs or FinFETs or maybe HEMTs. It's a micro photograph of LNA chip. Since our topic is advanced devices in modern electronics, so these are the LNA ICs being manufactured with the help of new devices. Unfortunately, there is no solution to the inductor. Inductor can be formed by this way only, the passive spiral structure of the copper or aluminum. Therefore, these are the inductors manufactured inside the IC, but remaining these all are the devices, maybe HMTs, FinFETs, MOSFETs. Fine. This is the comparison of all devices put together. Graphene FET, and at the end, there is a quantum device. Speed and quantum, I could not cover here. Those are available in PPT, but not explored here, not narrated here. Red figures show that who is the best. As far as speed is concerned, graphene FET is really very good. Gate all around is very good, as well as HEMT is very good, and quantum device also is very good. As far as power dissipation is concerned, MOS to memory stir is very, very good. Tunneling type of FET is very good as per dissipation, and quantum device is very good. And I will not read it out because of limitation in the time. The applications I mentioned here, the geometry, what kind of geometry technologies there, 2D, 2D, 3D, or tunneling effect phenomena are mentioned here in the comparison of devices. Therefore, this table is a summary of all devices put together. This is the tentatively conclusion for this presentation of 1.5 hours. Purposely, I will read out every word. CMOS is proven and mature technology. It dominates in low power area up to 5 gigahertz. However, it has its own limitations. Graphene, FinFET, gate all around FET, tunnel FET, high electron mobility transistors, GN, SOI, silicon on insulator, spintronic, quantum devices are the good candidates. Many of them are being matured. Strong foundation as a faculty, as an industry person in audience, if you want to go ahead with the career in VLSI because of the foundries, and it is endless and well reputation you will get if you are from the core VLSI field in the society, industry, everywhere in the research domain also. The strong foundation, but you will need the strong foundation of physics, materials, no doubt electromagnetics also, and the mathematics is needed. It is purposely I mentioned here this statement that the day will come, not the day will come, the era has come now. The designers are really sitting with the Mendeleev's periodic table, that how many elements are there, how many compounds are there, and which compound can offer better value of Epson R, which compound is good for tunneling effect. In this way, the materials are chosen and the devices are invented. Therefore, that means you will need the Mendeleev's, you need the chemical composition, the chemical properties, some idea of this, and these all about domains to become a really good researcher or good industry person, good professional in the VLSI semiconductor field. And then it has got good, very good opportunities and career in industries and research. It's all about the conclusion and the content, what the coordinator has told me. I think I tried to cover the devices which are very much matured nowadays, being matured nowadays, and very shortly they will be mature in case of chip manufacturing. It's all about this. If you have all the doubts we cannot attend here, cannot address here, if prominently, if any doubt is there, you can ask. Any question?
In the chat, I see one question. For which applications in this LNA chip best suited? 5G, Wi-Fi, GPS, or IoT?
LNAs are there for 5G. 5G as well as all. See, LNA is the block, low noise amplifier, low noise block, LNB is a typical amplifier, front end amplifier after receiving antenna. Therefore, LNA is a very useful element or circuit in cell phone, in satellite receiver, in cable TV receiver, in space stations, in base stations, in space vehicles, everywhere. Whenever there is antenna, receiving antenna, we need LNA. Therefore, these LNAs based upon the type, if it is a military vehicle and something dealing with the really Q band and frequency is more than 100 gigahertz, then the material is HEMT. Devices are HEMT. If it is something X band, something S band, something C band, FinFETs are enough. Therefore, depending upon the type of application, the LNA will consist of the devices accordingly. I
Yes,
think
sir. Correct.
I tried to answer the question.
Yes, sir. Yes, sir. It was best session. Like academics like us, we don't know what exactly is going on, and you have very well bridged it. Any more questions? You can unmute and ask. We can take one or two questions.
Yeah, I think they will have the questions when they will go through PPT in detail.
Yes,
Uh,
yes, yes.
after a lot many
So
days,
that is why
yeah,
they have asked for
good.
the PPT also. So I'll be
Yeah,
sharing the PDF of whatever you have sent, sir.
yeah. Okay,
Right,
okay,
sir.
okay.
Right,
I'm
sir.
I'm really very thankful to, no doubt, these the figures, we have to go get the figures from the Wikipedia and from the books available, soft copies. No doubt. Therefore, I'm really thankful to those all book authors, all those websites, the unknown persons who are there involved in the Wikipedia development, and no doubt our all fundamental VLSI electromagnetic physics books. This is
Yeah.
summary of all these things put together. Yeah.
Yes, so it was lot of efforts and your expertise which could bring such a big and vast knowledge in this PPTs. Really hats off to you, sir. I feel then we should go for a vote of thanks. Um, So, like, we would like to express our sincere gratitude, sir, for being our esteemed guest of honor for today's ATAL faculty program. Your profound expertise in mixed signal VLSI design chip and basically role as a member of board of studies added great academic value to the session, sir. The lecture on semiconductor devices in modern electronics offered deep insights while beautifully connecting fundamentals with current technological advancements. So it is only academics which helped you to interconnect the current technology with the academics, because it is very difficult for us to bridge this. So the clarity, experience, and practical perspectives greatly enrich the learning experience of all the participants. So once again, on behalf of the organizing committee, we extend our heartfelt thanks to you, sir, for your invaluable contribution and inspiring presence. Like, we couldn't give justice to what actually you were presenting. Like, you had to skip the quantum, but then I feel we can have your quantum session again, in which you will be able to elaborate more on that. So once again, thanks a lot, sir, for accepting the invitation and sharing your expertise and collecting all the data together in a precise and explained very well, sir. Thank you once again, sir, for that.
Thank you. Thank you.
So I feel without taking a break, can we proceed to the next session? Okay.
Yeah.
Uh,
Yeah. Okay.
yeah, thank you, sir.
Thank you. Thank you. Thank you.
I feel the next speaker is joined. Torkare sir, he's joined.
Yes, ma'am, I'm there.
Ah, welcome, sir. Again, privileged to have you on this platform. So, without wasting time, I would like to briefly introduce our guest of honor today. Dr. Ganesh C. Patil. He received his Bachelor of Degrees in ENTC from University of Pune. And again, our proud alumni. Hats off to you, sir. He completed his MTech from College of Engineering, Pune. After his MTech, he completed his PhD in the area of microelectronics. It was in 2014. Microelectronics and VLSI from IIT Kanpur. Then he bagged Best Student Award at Fourth International Student Workshop on Electrical Engineering at Kitsu. I'm sorry, I couldn't pronounce it properly. University of Fukuoka, Japan, and also received cash award of 20,000 twice by IIT Kanpur for publishing the paper in a reputed journal. He is reviewer of various SCI listed journals and also has worked as technical program chair for various IEEE international conferences. The area of his research work is device physics and modeling, novel nanoscale MOSFETs, analog digital CMOS circuits, VLSI system design and organic electronics. Dr. Patil has published several research papers in various reputed journals and more than 30 research papers in peer reviewed international conferences held at USA, Japan, Egypt, Singapore, India, and China. He is having total teaching experience of 18 years and currently is working as an associate professor at Center for VLSI and Nanotechnology at Vishweshwarya National Institute of Technology, Nagpur. So, without wasting more time, we would like to hear more from you, sir. With this brief introduction, I would like to welcome a heart warm welcome to Dr. Patil, sir. And the stage is yours, sir. Eagerly waiting to know more about this session.
Yes, yes. Thank you, ma'am, for this introduction. It gives me great pleasure that I'm able to present the talk in front of my teacher. I mean, who taught me VLSI in my when I started my career. So I will share my screen now. I hope this screen will be visible. Is the screen visible?
Not now. Yes, it is. You can make it
And
full screen.
I made the full screen as well.
Right, sir.
Yeah. So thank you everyone. Today I'm going to give you the glimpses about the nanoscale MOSFETs. So I'm going to just tell you about the what so far happened in the past related to the nanoscale MOSFETs, then the present scenario, and also I'm just trying to tell you some research areas where you could start your research in this domain. So Actually, I'm the core device researcher, and the bread and butter of the device researchers like me is the devices. So you could see, I mean, today the technology is changing. I mean, when we started with it was the 10 micrometer was the channel length, and today we are reaching to the 1.2 nanometer. So my friends, actually in one of the conference I attended at IIT Chennai, and the minister told that there was one bus came. The name of that bus was the microelectronics. So in the year around 1980, the microelectronics came. A similar kind of the bus came in the year 2010 as well, and the name of that bus was the nanoelectronics. And at that time, the government of India took the different decisions, and they started forming the INOP centers. The INOP is the International, I mean, Indian Nano Electronics Users Program. So, government of India spent around 300 crores to IIT Bombay for establishing the lab, and 300 crores for the IIC Bangalore also to make the sense sensor center. So the idea was the IIT Bombay will work on the devices and the IIC Bangalore will work on the material side, and that is what the this kind of the research Indian government started. My friends, today the similar kind of the bus has also arrived, and the name of that bus is now Quantum. So actually, there is quantum electronics, you could say, or most of the time people name it as a Armstrong electronics as well, or the quantum technologies as well. That is what the government of India started the National Quantum Mission, and since I'm the part of the one of the committee in the National Quantum Mission, I'm just like to tell you that you people could catch the bus now which is running in India, and that is quantum electronics or the quantum technologies. So before start of the talk, I will just tell you, I mean, what I'm going to talk today. So basically, you could see the kind of the technologies today where we are using the mobile phones and all the appliances. My friends, if you remember, right, if morning 6 o'clock you wake up and at night 12 if you sleep, you could see how many electronic gadgets we are using in our day-to-day life. So the number of electronic gadgets which we are using today are pretty high. And I mean, unfortunately, in India, we could not able to fabricate the integrated circuits. But now the Indian government took the initiatives and then we started the development of the fabrication laboratories also. Not only fabrication of the state of the art integrated circuit like 1.2 nanometer scale or 1.8 nanometer scale, but we started fabricating some of the ICs. We had one semiconductor complex at I mean Mohali, Chandigarh, but that technology is having the channel length of around 180 nanometer. But still, we are using this, and we'll have to come up with the new technologies. And the semiconductor hub is now pretty coming up now, and we all the engineers have to work on the semiconductor domains now. So the if you see the VLSI domain, there are three basically abstraction levels. One is the device, second one is the circuit, and the third one is the system. So the VLSI domain is divided into these three abstraction levels. Today I'm going to focus on the first abstraction level, that is the device. So you could see here the key part would be the motherboard, and on this motherboard the tiny block which we could see would be the processor, that is the Intel 4. My friends, if you remember, if you see the time gap between the development of the processor, when we talk about the 4-bit processor like 4004 and the 8080 or 8085, the time gap between the development of these processors were around 4 years. Because those days when people were starting of fabricating such a kind of the processors, they have to do the paper and pencil approach. So as usual, we will have to design a digital logic circuit. We'll have to design it on the paper, then put it on the breadboard. Then we'll have to connect with them with the single strand wires. After doing all this kind of the stuff, they'll have to send it for the foundry for the tape out. The chip would come up, and after fabricating such kind of the chip, if there will be any fault is there, there is no choice. They'll have to throw it away. That is what the gap between the development of the 4-bit processor like 4004 to 8080 is now was the 4 years also. But today if we see, we have the gap of just 6 months, or we could say the time gap between P1 and P2, Pentium 1 and Pentium 2, is just 6 months. So this is mainly because of the VLSI developments and the EDA tools which we have developed. I mean, people have developed. Also, not only for the software development side, people have also did the development at the hardware side as well. I mean, there was a monopoly of like Intel those days. Now today the monopoly of the Intel has already been broken, and now instead of talking about single core on the silicon die or the tiny silicon die, we are talking about 5,000 cores are there on a single tiny silicon chip. And now the market of the Nvidia is coming into the picture. So my friends, for the development of the processors, we require a simple tiny block, which is the working horse of the today's semiconductor industry, and we name that working horse as a MOSFET. So my friends, I'm going to talk about that working horse, which we call it as a MOSFET. So this MOSFET look like, there will be a source, drain, and the gate. I mean, these are the three electrodes. This is just a sample snap of the, a 90 nanometer process which have been developed. So there were developments not only at the computation side or the IC development side, the developments happen at the MOSFETs as well. I mean, when the first major breakthrough happened, that major breakthrough first happened in the year 1947. All of you might be knowing. I mean, the year when our Indians were fighting to get the freedom in the year around 1947, but at the Bell Laboratories, Bardeen, Brattain, and the Shockley, they come up together and they come up with the germanium point contact. Bipolar junction transistor. So it was the first major breakthrough in the semiconductor industry, and people started doing in research in the devices and the integrated circuits as well. The second major breakthrough happened when the Jack Kilby come up with the planar process flow. Actually, the MOSFET which I am showing now that has been developed in the year around 1935 by Lilienfeld, but it was not being considered as a major breakthrough because if you see the device, at the device there will be a lot of surface states were there. I mean the SiO2, the silicon dioxide, there were a lot of surface states were there. The mobility was the issue. So to tackle that problem, people thought, okay, the MOSFET will not be the popular device, but the BJT came into the picture. But when Jack Kilby come up with the planar process flow, so people thought, yes, MOSFET could be become the working horse, and the most of the research started doing in the MOSFET era. And they started with the 10 micrometer channel length. Channel length is the distance between the source and the drain. So it was 10 micrometer, now it goes to the 5 micrometer, then it goes to the 2.5 micrometer, then 180 nanometer, then again 120 nanometer, 90 nanometer. When 90 nanometer was the channel length reached, people thought that it could not be further scaled down. But people didn't stop because it was the bulk MOSFET. Then the new technology came, and the name of that technology is silicon on insulator. Then SOI came into the market. Not only SOI, then again scaling started 90 nanometer to 65 nanometer, from 65 nanometer to 45 nanometer. When it reached to the 45 nanometer, it is the now third major breakthrough happened in the semiconductor industry, and that third major breakthrough was the invention of the FinFET, right? That FinFET was a kind of the transistor, and then people started using the FinFET for the further scaling and the IC development. Though it reached to the 45 nanometer, to it reached to the 32 nanometer. After 32, it goes to the 22 nanometer. It goes to the deca nanometer, means 10 nanometer, then 7 nanometer, 4 nanometer. After 4 nanometer, 2.8 nanometer, and 1.8 nanometer. And my friends, today we are at the 1.2 nanometer channel length. So you could imagine how thin that device would be. And this 1.2 nanometer is the channel length, means the distance between the source and the drain. My friends, you could see that our hair diameter is a 50 micrometer. You could imagine our hair diameter is 50 micrometer, and then when we talk about nanometer, that is 1,000 times less than this. How thin that device would be, or how thin that ICs would be, or on the single tiny silicon die, how thin that devices would be, which we are integrating in our semiconductor integrated circuits as well. So that tiny device today we are going to talk about, and I'm going to tell you what is the future research of this device today. So this is the source, gate, and the drain, and this is the channel region. And this MOSFET is like, it is a kind of the tap. And this tap control could be done by this gate, that is the gate control. My friends, this tap control would be going to control the water, I mean the flow of the electrons from the source towards the drain, and that will be controlled by this gate. So this gate would have the different junctions also. I mean, if you talk about the why the name is given to this device as a FET, the reason was the device is the voltage controlled device. And since this device is the voltage controlled device, voltage is related to the electric field, and that is electric field will be minus dV by dx. So that is what the name is given it as a field effect. And transistor, the name of the transistor is transfer of resistance. So this device is used for the current transport, right? Transfer of resistance. So this is a field effect transistor. And as we go on changing this gate control, the name of the different fields will come up. Let us say, for example, at this gate control, if I'll be using a junction, I mean PN junction kind of the diode, if I'll be using, it will be called as a JFET. If I am using at the juncture of the gate, if I be using MOS junction, metal oxide semiconductor junction, it would call as a MESFET. At the juncture, if I be using metal effects, right, MS junction, metal semiconductor junction, it will be named as a MESFET. Or even if you try to use the juncture at the hetero junction, it will become a high electron mobility transistor. So just now I was just listening the talk by Professor Mali. He was talking about HIMT, right? So that HIMT is a kind of a device where the heterojunction is used at the control of the gate. So as we change the gate control, the type of the field effect transistors will going to change. So today I'm going to talk about the first basic device, that is the MOSFET. So the field effect transistor has the source, drain, gate. There are two different electric fields have been applied. The first electric field is the vertical electric field. When we apply the bias at the gate, that is VG, that electric field will be a vertical electric field, or that is also the perpendicular electric field, because it is the surface device. So at the surface of the device, there will be perpendicular electric field. The second electric field is when we try to apply the bias at the drain, that is VDS, that drain bias will work like a lateral electric field, or it is also work like a horizontal electric field. So this device is operated with the two different electric fields. One is the vertical electric field, which will create the channel at the between the source and the drain, and the lateral electric field. That lateral electric field will allow the transport of the current from the drain to the source, and the transport of the electrons from the source towards the drain. So the source drain contact should be very conductive, and obviously the channel will limit the resistance, and the gate will control. The gate will go to create the channel. So that is what the gate controls, the resistance of the FET. So today, if you see, there are different transistor aspects are there. The molecular motors are there. Now today we are using the biosensors, and also we are talking about the spin memories also. My friends, in the memory also there is a lot of revolution, or innovations happen. We started with the 6 transistor cell, which was SRAM. Then we come up with the 1T, 1C, 1 transistor, 1 capacitor cell, that is the DRAM. Then today people are talking about MRAM, that is magnetic RAM. Not only MRAM, today people are talking about RRAM. RAM stands for the resistive RAM. Now it is opening the different areas for the research. Now spintronics is the one of the domain where people are working today, that will be talking about the spin memories. The electron has the up spin and the down spin. So spintronics is the upcoming area where the people are doing the research. Not only this, people are today are talking about the molecular electronics or the molecular dynamics as well. So the molecular electronics means the channel which we are talking about, the between source and the drain, that channel will be also made up of only molecules or the atoms. That kind of the technology coming would be the molecular electronics, where people are trying to do the research. Now, if you look at the field effect transistor, it has the source, drain. Obviously, as I told you, there are two biasings are there. One is at the gate, another would be at the drain. Obviously, so there will be two different IV characteristics will come up. My friends, for any device or for electronic device, the basic tool for analyzing any device architecture is only the IV tool. How the voltage change, if voltage changes, how there will be change in the current. You look at the diode, PN junction diode, we'll have to characterize IV. If you look at the BJT, we'll have to characterize the IV. If you take any kind of the device or MOSFETs or maybe BJT, maybe IGBT, maybe SCRs, the only tool to analyze any device would be only and only IV. You voltage change you do, and look at the change which is happening at the in the current. So like this, in this device, that is the field effect MOSFET, we have the two voltage changes we are making. One is at the vertical electric field we are applying, that is the VGS we are applying, and the second bias which we are applying is the VDS, right? So obviously there will be two IVs will come up. One would be the change in the gate voltage, where how the current will going to change when I'm changing my gate voltage. So the main change would after happens because of the threshold voltage when the channel would be get formed, and the device will become turned on. And the second characteristics will be, once the device will be turned on, when channel will be get formed, then as I'm gone changing my drain bias, then current will start flowing. This MOSFET would have the two important regions. One is the linear region and the second one is the saturation region. My friends, This MOSFET would be work like a power dissipator or a current source as well. I mean, it could work like a current sink. Current sink means it will be it will taking a current like a resistor takes. So once it operates in the linear region, it could be a power dissipator or it is current sink. And once it is operated in the saturation region, this MOSFET will work like a current source, because current will be constant. Now that will be the drain saturation current, which will be constant. Current source could be also we could use as a MOSFET. So this is the two important characteristics. So before understanding any MOSFET, these two characteristics are most important to study. And the major driving force for this microelectronics is done by the Moore's law. Already is famous. You could see the trend, it has been changed. I told you about 4004, and now people are going for the not only one core, single core, dual core, quad core, octa core. My friends, 5,000 cores are there in a single tiny silicon die. That is the innovation happen in the semiconductor industry. And this fellow Moore told that there will be, it will double, the number of transistors will double right after 1.5 years, and it happening now. It happened also in older days as well. So how far we could scale the transistors now? Actually, there is a window. That window separates the microelectronics and the nano electronics era. So the devices having the channel length above 100 nanometer, they are called as the microelectronics, and when the channel length is below 100 nanometer, that era is the nano electronics. And one more era now started coming, that is angstrom electronics, where the channel length would be 10 to the power minus 10. Right, 1 angstrom means or 10 to the power minus 10. So that will be the new upcoming era where people will start doing research. So when we talk about microelectronics and the nanoelectronics, there will be new physics would come up. And since the channel length is around in the nanometer region, obviously the classical physics which we have studied so far, the current transport which we have studied so far, that was the drift diffusion, right? That was classical physics was telling us the electron is like a particle. The electron is like a car moving on a road. And that is what, for that car moving on a road, we were talking about the force, we were talking about velocity, we were talking about acceleration. I mean, that phenomena was there because so far the device physics or the classical physics which we have studied so far for the device analysis, it was the Newtonian mechanics. But my friends, now when we talk about the scale channel length around 1.2 nanometer, the Newtonian mechanics will not work, and the new mechanics will have to work. That mechanics would be quantum mechanics. I mean, that has been developed by the Schrödinger. Actually, the day when the Schrödinger went to the conference in France, and he was telling, this electron would have the duality. I mean, it has the electronic particle nature as well as it has the wave nature. But in the France, nobody accepted, whatever Schrödinger is telling is of no use, because the electron is like a just particle. Even Einstein refused to accept his theory, what he proposed. He was telling the electron would have the wave nature, the electron would have the particle nature as well, but nobody accepted those days. And but the theory he proposed was the equation of the motion, and the equation of the electron motion was the Schrödinger equation. But afterwards, it has been supported by the de Broglie. De Broglie come up with the de Broglie hypothesis. He told no, there will be presence of the wave nature as well. Then it is been supported by the Planck. Planck come up with the Planck's constant. It has been supported by the Heisenberg. Heisenberg come up with the identity that we call it as a Heisenberg identity, uncertainty principle. So you could see the black body radiations also. I mean, if you take a metal like iron and if you heat it, you could see a reddish color on the metal. So what that effect is? That effect is the black body radiation. Means those days whatever Schrödinger has explained about the quantum physics and the quantum mechanics, it has a worthwhile physics. But now and today we have to use this physics what Schrödinger has told us to do. And people are today talking about the quantum computing, quantum mission, and our Indian government is also taking a role in the development of the national quantum mission as well. So my friends, when we scale down the transistor at the nano dimensions or the angstrom dimensions, we'll have to talk about the new physics. This is just a simple snap of the transistor which Intel developed, MOSFET, that is the 2003 Intel 2003 transistor, then 6 nanometer transistor at IBM. Then this is the IEDM is one of the conference worldwide held that is called as IEEE Electron Device Meeting. In that meeting, then Uchida come up with this 0.7 nanometer thick MOSFET, and now the smallness would lead to the quantum effects, and the quantum effects will be come up with the quantum confinement, atomistic fluctuations, leakage, tunneling, quantum scattering. So these are the phenomena which we'll have to study to come up with the new device architectures. So the basic problem for the today's, you people could note it down. The major challenge for the semiconductor industry and the devices is the leakage power. My friends, you could see the kind of the power dissipation which we have here. When we talk about the Pentium one, it was around the 10 watts per centimeter square. But as we scale down the transistor to P2, P3, the power dissipation, mainly the power density, particularly leakage power or static power, is reaching to the nuclear reactor power dissipation, or soon it goes increase, like it will reach to the rocket nozzle or sun surface as well. So the major challenge for the today's semiconductor industry is the leakage power density. So we'll have to come up with the new materials, new devices, new architectures, so that the leakage problem could be solved. If you see the scaling trend, the power density, when we scale down, the passive power density is increasing as we scale down the channel length, right? When we were around 0.1 micrometer, the power dissipation was like this, but when we scale down to 0.01 micrometer, the power density is increasing. And if you see the trend for the active power dissipation, that is the dynamic power dissipation, dynamic power dissipation is mainly because of the switching activity in the MOSFETs or the CMOS logic circuits. So you could see here in these domains, the static power was the lower than the active power. But now if you see, when the scale dimensions are reached, the static power, means leakage power, is becoming closer to the active power, even more than that, right? So the power density change is the major challenge. You could see here, when we are talking about 4004 processors or even P1, it was around 10 watts per centimeter square. But as we are gone scaling down, the power dissipation is increasing tremendously. So that is the major challenge. Now, there will be one question maybe coming in your mind, ki, why people are go with the dual core, quad core, octa core, hexa core, even 5000 cores together. And the main reason was the power dissipation only. If you see here, as per this result, right, the power dissipation, when we are in the single core, it was around 100 watt per centimeter square. But when we have the core, two cores are there with the same battery voltage, now the concept of the parallelism came. Now let us look at this snap. This is the animated graph. You could see when we have the single core, right, that will operate at the lower VDD, and if you use the dual core with the same energy, now we could run two operations parallelly. That is what the to solve the problem of the static leakage, power dissipation, the concept of the dual core came in the processors. And now actually, if you see the research domains, people are working in the RAM memory side and as well as the computation side. So if we have the more cores, the computation speed will be get increased, and to achieve this, we'll have to have the compromise with the leakage. But now with this double core, we could the same performance we could achieve at the similar kind of the power dissipation. You could see in the other graph at the left side, we will have the two cores, the power dissipation will be lower than the 100. And if you go with the single core, it could go up and up. It will reach to the around 1000, maybe 1000 watts per centimeter also. So the concept of the dual core or quad core came to solve the problem of the static power dissipation, and the concept is the parallelism. So if you see the bulk MOSFET structure, there are a lot of bulk MOSFET scaling challenges. Let us say, for example, if we scale down the VDD, then IOF would shoot up, and the power dissipation is IOF into VDD. So when we scale down the VDD, I mean, ion will try to improve, but at the same time, IOF will also improve, and that will lead to the VT trade-off, that is threshold voltage trade-off would come up. So there will be always trade-off between ion and IOF. Ion will improve, at the same time IOF will improve. My friends, I mean, if you try to look for the logic families, right? So I hope you could answer my question. Can I ask one question quickly, ma'am?
Yes, yes, you can ask.
Yes,
By all
yes.
means.
Dear audience, just I wanted to keep you alive. Otherwise, I'll have to feel I'm just talking to the computer, right? To solve this, I mean, I just wanted to know, okay, how many of you are listening to me. Otherwise, it will be you stop my time as well as your time as well. So my simple question is, my friends, what are the figures of merit of digital logic circuits? Any quick answer? Yuvraj sir,
You can
maybe
put
you
it in
could
chat.
unmute the mics so that
Yeah, yeah.
audience could answer.
They can put it in chat also, or they can
Yeah, yeah.
unmute and tell.
Yes, yes.
Can you repeat the question?
Yeah. What are the figures of merit of
Sir, you have Ganesh, sir, you please unmute yourself. You unmute yourself. Ganesh, sir.
you?
Yeah, 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 you are unmute.
Yes. Yeah. Can you anybody tell me what are the figures of merit of digital integrated circuits?
Are they understanding the question? Yes. Can you read in the chat? You are getting the answers.
Oh, okay, okay. I will see in the chat. Oh, I will just scroll down. Yeah, somebody told speed and power. Yeah, correct, correct. Yes, Mrs.
Next is
Bhat Lavande told it is speed and power. Yes, correct. So thank you, ma'am. The other part will be if we try to consider the TTL logic family and the CMOS, what TTL logic family has? So TTL logic
two
family
more
has the
answers you have, sir. It's propagation delay into power dissipation, or then power dissipation versus speed of circuits.
yes,
It's
yes,
one and
yes,
the same, like, yeah.
yes, 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 yes. Thanks, thanks. So I'm just continuing my session now. I hope you are listening and you are understanding this. So I was telling you the detailed logic family has high speed. At the same time, it has the high power dissipation. So detail has high speed, at the same time high power dissipation. But if you consider the CMOS has low speed as well as it has the low power dissipation. And the CMOS, the reason for having the low speed is because it has the capacitances are involved. I mean, that would be parasitic capacitances are involved. So in BJT, bipolar junction transistor, I mean TTL transistor logic is based upon the BJT. So BJT has the less parasitic capacitances than the MOSFET. So BJT is used for the TTL family. So that is what I just wanted to ask. So speed and the power, these are the two important figures of merit where people are working. The same way, this ion and IOF are the two important parameters where people are started designing the transistor. Because if you see the propagation delay is inversely proportional to the speed. So if you wanted to improve the speed, you'll have to reduce the intrinsic gate delay or the gate delay or propagation delay we could call. And propagation delay is equal to Cg into VDD by ion. So ion is at the denominator side. So if you wanted to reduce the intrinsic gate delay, you'll have to improve the ion, right? So if you improve the ion, intrinsic gate delay will reduce and the speed will improve. But when we reduce the when we try to increase the ion, at the same time IOF will also increase, and since IOF will increase, the power dissipation is the product of IOF and VDD, right? So static power dissipation will also increase. So there will be always trade-off between speed and the power, and always trade-off between ion and IOF. So when we start doing any transistor research or the device research, people trying to address the challenges for the ion and the IOF as well. You could see in the simple equation of the drive current, right? This ion, if you wanted to improve, you'll have to scale down the LG. So that is what people started scaling down the channel length. And not only this, this VTH also will have to reduce. But when we reduce the VTH, this IOF will also improve. So there will be always scaling challenges are there. To address the challenges, people come up with the new technologies. So we require the new transistor structure. This is the bulk MOSFET structure. You could see here source, drain and the gate, there is a channel length. So to solve this, off-state leakage must be suppressed when we scale down. As I told you, when we scale down the channel length, the ion will improve, but at the same time, IOF will also improve. So we'll have to put our efforts to reduce the off-state leakage, that is IOF. And that is what we'll have to do the reduction in the VT and hence reduction in the VDD as well. But this leakage region is also the challenge now. So to solve this problem, people told that why don't you not only change the channel length, we will make a thin body as well. So people come up with the ultra thin body kind of the devices. So this is the kind of the structure of ultra thin body devices. But the ultra thin body devices would have the threshold voltage challenges, there will be variability challenges, there will be random dopant fluctuations will be there will be line edge roughness is also another challenge. So to address the challenge, people thought that why don't we use the intrinsic channel? Intrinsic channel means it is the channel without doping. This is undoped channel. So people come up with the undoped ultra thin body kind of the bulk MOSFETs. So not only this, the people started doing this because they wanted to scale down, and the ion they wanted to improve, IOF they wanted to reduce, speed and the performance, speed and the power they wanted to address. So the new architecture came, as I told you, after 90 nanometer technology, and that technology was the silicon on insulator. Means why don't we put the undoped silicon on the buried oxide, that is box. Buried oxide is also made up of the SiO2, and that technology is the SOI technology, and they come up with the two kind of the devices. One would be partially depleted SOI, then the fully depleted SOI, and that SOI technology play an important role now. So to address any ITRS requirement, ITRS stands for International Technology Roadmap for Semiconductors. The older days it was ITRS. And since I'm showing you the slide of around 2007 publication, I mean today people are calling it as a IRDS. I mean ITRS is gone now. IRDS came up. So actually, for as I told you, our electronic equipments, electronic gadgets, we have the high performance, we require the low power, or we could have a low standby power, like mobile phones. Mobile phones would be some of the time go in the sleep mode, right? When they will go in the sleep mode, we don't require that kind of the power, right? Or we don't require that kind of the performance. But if you look at the servers, right? Servers, we could not compromise with the performance, right? Power we could compromise. If we have the I mean high leakage, still we could compromise. But it is mandatory for us to have the highest ion so that the performance could be get improved. At the same time, look at the laptops or other performance, these are low operating power. So that time, I mean, if it has a medium ion, so medium CV by I, which is intrinsic gate delay, right? So or medium leakage, still we could work. But like our mobile gadgets, right? We are operating in the low standby power. So it should have the lowest leakage, low ion and high VDD, right? So these are the ITRS requirements which we are addressing for the CMOS applications. And the major technology innovations over the few years happen was people come up with the polysilicon, silicon on nothing, silicon on insulator, already I told you, they come up with the planar bulk MOSFETs, ultra thin body FDSOI, double gate FinFET, right? And there will be different paths parallelly people have made for the innovations. And what are the future devices? The planar devices, then as I told you, ultra thin body, FDSOI, then double gate FinFET, and there would be new era would come up where we require the alternate materials like germanium 3-5 semiconductors, or we require the nanowire transistors as well. My friends, today the integrated circuits we could see they are all made up of the silicon, right? So silicon has the God-gifted property, and that God-gifted property is formation of the native gate oxide, that is SiO2. And when we talk about the planar IC process flow, we require the SiO2 in between. So since the silicon has the God-gifted property of forming SiO2, when we keep the silicon vapor in the environment, it will be forming a SiO2 layer on top of it. That is what silicon is the mature material. But in future, as technology will going to change, right? So people are come up with the new materials also, right? Because in future, silicon may die, right? So silicon may die, but when silicon will going to die? Silicon will going to die in future when people will reach the channel length around the silicon bond length. So if the silicon bond length up to that people have scaled down, definitely the silicon will going to die. And when silicon will going to die, we'll have to come up with the new alternate device materials. Not only device materials, we'll have to come up with the new device architectures as well. And that is what people started doing the new devices. So these are the technology innovations so far. We saw about the, silicon germanium, then FinFET already we reached, FinFET already people are using. Now we are talking about beyond CMOS. So the new devices will be spintronics, tunnel FETs, not only nanowire FinFETs will come up, and then multi-gate field effect transistors will come up, high-K materials will come up. And not only this, we'll have to enhance the mobility also. So to enhance the mobility, instead of silicon now 3-5 semiconductors like gallium arsenide, right, will be the new future 3-5 semiconductor materials for the new devices. So these are the technology innovations that will be beyond CMOS. So by the way, as I told you about the device abstraction level, we not just want to develop the device, but we'll have to also look for what kind of circuit we are able to develop, right? So for digital circuit requirements, if you look at, we should have the high ion-off ratio, then we should have the low intrinsic gate delay so that the speed will shoot up. We should have the low short-term effects like drain-induced barrier lowering, subthreshold swing. You should have the low parasitic resistance in the capacitors. And the most of the devices so far people have studied was the PDSOI, partially depleted SOI, fully depleted SOI, double gate, undoped ultra thin body. Then, but what about the analog RF requirements? What about the analog RF performance? My friends, today people are talking about digital CMOS, but what about analog CMOS? What about the RF CMOS? So will the MOSFETs will able to cover the challenges of the analog CMOS? Because as I told you, when we are talking about analog and the RF circuits, the capacitances are the key players over there, right? Whenever there are capacitances, there will be frequency change. And as I told you earlier also, the problem of the MOSFET is it has the parasitic capacitances. So can we able to use the MOSFET for the analog CMOS also, or as well as RF CMOS also? Still, most of the application people are still going with the BJT because speed is the major constraint, right? Frequency is the major constraint. Since the MOSFET has the high parasitic capacitances, still people are looking research how these MOSFETs could be used for the analog and the RF application. So there are open challenges are there, some few challenges are also there where people are trying to address the analog and the RF systems also, because today the we are reaching to the terahertz kind of the technologies, or when we talk about the terahertz kind of the technologies, we require the high frequency devices, and that can we able to reach that frequency with the MOSFETs. So these are the again challenges for the analog and RF applications. So these are the analog circuit requirements. As I told you, for digital circuits, speed and the power, these are the two figures of merit. Similarly, for the analog circuit application, two figures of merit are the gain and the bandwidth. So as there is a trade-off between speed and the power for digital, similarly for analog also there is a trade-off between gain and the bandwidth. As we try to improve the gain, bandwidth will become low. When we try to improve the bandwidth, gain will go down. And the gain and the bandwidth for particularly for the MOSFET is related to the transconductance and the output resistance. So the DC gain would be Gm into R out. The cutoff frequency would be of T. We should have the high signal swing, linearity, low noise. These are the again challenges, and these are the requirements for the analog circuits. There is also trade-off between the analog design also. If you reduce the TOX, we'll be getting the increased gate control, but it also increases the gate leakage currents. Similarly, if we lower down the channel length, then short channel become worse, and again which will be also reduce the R out. And when the R out will be changed, then the gain will be also get affected. Similarly, once we do the source drain engineering, right, when we have the long-term MOSFET, the source drain resistances was not taken care because the channel resistance itself was larger than the source drain resistance. But when we reduce the channel length around 10 nanometer, the source drain these resistances are more than the channel resistance as well. So source drain engineering people are trying to do to reduce the source drain resistance, specifically the source drain resistance at the source and the drain. So these are the new alternative device architectures, right? That will be coming up now. So we require the new device architectures and the materials. So obviously we require the high mobility transistors in future when we scale down for the new technology nodes. So how can we push this technology? So we require a better FinFETs now. We require the multiple gate architectures, and we require the better field control. So we require the new better materials. Silicon is already reaching now, but people also don't want to compromise with the silicon because lot of foundry are using silicon setup only. And let us say, for example, if you not use the silicon, if you go with the other material, crores of rupees of foundry they already established. So who will going to use this whatever the foundry setups they made, right? So people are looking for the any alternative material for the silicon also, and they are coming with the new silicon polytype that is called as a silicene. Like graphene, right? Phosphorine, germanium, stannine. So these are the new upcoming materials people are looking for. They call it as a 2D materials, right? Like 3D. 3D means X, Y, Z dimensions. For carbon, we could say graphite is a 3D material. Like one of the dimension of the, if you reduce lower than the de Broglie wavelength, it will be forming a 2D material like a plane, right? It will be forming a graphene. Or when we make a kind of a roll of this graphene, it will be forming a nanowire or quantum wire. It will be forming a carbon nanotube. And when we reduce that to all the three dimensions, if we reduce, it will be forming a dot. That is, we call it as a quantum dot. So there will be quantum dot, quantum wire, quantum well. So these are the different challenges, which people are studying now in the quantum physics. So the new upcoming material would be graphene, silicene, phosphorine, germanium. All these materials are the two-dimensional materials. So this is the material zoo. People come up with the strained silicon, that is silicon germanium material. Then they come up with the carbon nanotube as a channel. Then they come up with the silicon nanowires. Not only this, now people are talking about the molecular electronics where the gate and the gate will be controlled by the molecules. Between the source and the drain, there will be atomic layers would be there, and that is the 2D materials or the molecules would be become the channel for the field effect transistors. So the most of the research in 2010 people have carried out with the graphene. 2010 was the year where most of the papers were published on graphene. Now, because graphene is the kind of the structure, you could see graphite, the pencil we could use, this is the graphite. Now you could see here the plain material, that is the graphene, and when we mount it, it will be forming a single wall carbon nanotube or multi-wall carbon nanotube. So these are all carbon polytypes. So, but when we scale down to this, we require the atomistic models. So these are the kind of the structures we could form between the source and the drain, and the channel would be just a kind of a graphene plane, graphene ribbon, right? So these are the new materials people are looking for. Not only this, there will be innovations of the new principles like spintronics, multiferrites, nanomagnetism, and there will be formation of the MRAMs also that I already we had discussed. So I will just move ahead. So how do you model the today's semiconductor devices? So far in your IC designs, we were using the top-down approach. Means, I will just give the example. We were thinking about system, then we go to the circuit, then from the circuit we go to the device like transistor. That is the top-down approach. So far we were using the top-down approach. But for upcoming era, this top-down approach will not be going to worthwhile. We'll have to go with the bottom-up approach. Bottom-up approach means, first of all, we'll have to think about the material. Once the material will be get thought about, we'll have to think about with this material can we make a transistor, we could make a device or transistor, particularly field effect transistor. If you try to make a field effect transistor, with this field effect transistor, can you able to make a circuit? And if you are able to make a circuit, can you able to make a system? So far, traditionally, we were using the top-down approach, but in future, we'll have to go with the bottom-up approach, right? So for the upcoming nanoelectronics era, we'll have to use the bottom-up approach. And in the top-down approach, we were talking about the classical physics, that is the deep diffusion. Then we call about the Maxwell-Boltzmann transport we were talking about, and then we go towards the quantum transport, right? But when we talk about the devices now, we'll have to go with when we talk about the quantum transport, the quantum confinement effects would come into the picture, right? And these are the challenges now. Quantum entanglement is also the one of the challenge now. It is open challenge which people are trying to address. But now we'll have to come up with the bottom-up approach where we talk about the molecules, then the device, then the circuit, and then the system. That bottom-up approach we'll have to use in the coming future. And now this bottom-up approach will be come up with you could see when the channel length was more than the 1 micrometer, it was bulk solid classical deep diffusion phenomena we have used. When it is around 100 nanometer, we'll have to go with the semi-classical transport. And when we talk about molecules, we'll have to talk about the quantum transport. And the main challenge is, right, basic principle in electronics or the electrical, we use the Ohm's law, right? But the Ohm's law, it's just simple IV which I'm showing here. As I'm changing my voltage, my current is changing linearly, and the inverse slope of this is the resistance, right? Now, but the resistance R is equal to rho L by A, right? Rho is the resistivity, L is the length, and A is the area. So the dimensions were playing a role to decide the resistance R. But when we talk about the quantum dimensions, the geometry of the material or the geometry will not play a role because length would be very thin, area is also very thin. So in future, when we talk about quantum confinement or quantum effects at the nanoscale dimensions like 1.2 nanometer, then Ohm's law will not be used. So see, if you see this R is independent of the material geometry because it will just depend upon the Planck's constant H and the Q, that is the electron charge, right? So this Ohm's law will not be there for when we talk about the quantum confinement effects. Similarly, the Fourier laws which we talk about, they will not be there, right? So the new challenges will be coming, that will be atomistic effects will come up, and that atomistic effects leads to the different domains for the research. So this, if you see it from the scaling perspective, like or if you correlate the biology with the electronics, when we talk about trees, that is like a cell phone towers, human being like a server, human brain is like motherboard. Like this, a DNA will be gate oxide, carbon atom would be silicon atom, because we were moving from the macro tech to the nanotech, right? Macro, meso, micro, nano, because we are talking about dimensions around 10 to the power minus 9 or even 10 to the power minus 10. So the near future would be nanotech era, where people are talking about the devices and the circuits. So if you look at the electronics, the big picture is most of the time the people's work on the computations and the storage. The innovations in the semiconductor industry in the VLSI domain happen in the two domains. One is the computation, where people are trying to come up with the new processors, like we have the microprocessors, microcontrollers, digital signal processors, network processors, I mean system on chip now. People are talking about lab on chip now. I mean, these are all computations part, right? Or the second domain will be people are talking about SRAM, DRAM, flash, right? Or people are talking about NAND flash, MRAM, RRAM. I mean, these are the way people are doing the research. So electronics is research would have the computation and the storage. So these are the only two domains on which the all gadgets or applications we are looking into. And if you look at the microelectronics to nanoelectronics, so we require the new effects will come up, that is gate tunneling, tunnel quantization. The transport will be now a simple transport, it will be ballistic transport. So for that we require the new materials, we require the new device architectures as well. And the second domain would be, I mean, when we are talking about, because I'm just touching to my domain, which is my research area where I'm working on now. These are the sensors. So actually, as I told you, we could not able to fabricate the devices. Most of the time, my students go to IIT Bombay for fabricating. Part of the IUNP IIT Bombay. So most of the students go to IIT Bombay, they fabricate the devices over there and they will characterize it here in VNIT Nagpur, and we come up with the new device and the sensors as well. So as far as the CMOS sensors are concerned, sensors play an important role in our day-to-day life. I mean, you are this tiny block, this is the mobile phone. There are a lot of sensors are come up with. So new upcoming era for the device research would be sensors. So people are come up with the memory chips, they come up with the processor chips. Not only this, they come up with the network chips, wireless chips, and the domain which is open now would be sensor chips, particularly biosensor chips. So when we talk about the more than more, right? So we talk about the information processing, right? More than more means we talk about the analog RF passives, sensors, actuators, and the we'll have to combine the system on chip and system in package. All this will have to combine together to form the new integrated circuits. So we'll have to move towards the hybrid SoCs now. So far, in before 2000 era, we were talking about silicon CMOS. So we were talking about the technology drivers where only the memory and the logic gates. Then materials were silicon and silicon dioxide, silicon nitride, and the device architectures were the classical CMOS. But when we move between the era of the 20 years between 2000 and 2020, then there are new materials have come up, new technology drivers where again the memory and the logic, the materials will be silicon, some coexisting materials like silicon germanium, and the new device architectures where non-classical CMOS, non-CMOS like FinFET, kind of the devices we already developed. If you wanted to go towards more domain, we'll have to combine all these two domains together and we have to come up with the hybrid system on chips. So hybrid CMOS, hybrid SoCs will be, there will be silicon existing materials, polymers, piezoelectric materials, ferroelectric materials, magnetic materials, then memory alloys, and the device architectures will be existing, coexisting CMOS, MEMS, chemical sensors, biological sensors. Like in our mobile phones, we use the MEMS CMOS, right? So that would be the domain where people are trying to work together to come up with the new sensors, so that we could come up with the new hybrid system on chip architectures. So this is just glimpse. I will show you the new material domains. You could see the fourth column of the periodic table. We have the carbon. All the carbon polytypes people are already being studied. There was a graphite. There was the graphene. There is the carbon nanotube and the carbon dot. I mean, like C60 is the fluorine. Like this, we have the silicon, right? Then we have the germanium. Like this, we have the combination of the fourth also silicon carbide, silicon germanium, right? Then we have the 3 5 semiconductors like aluminum phosphide, aluminum arsenide, gallium arsenide, indium phosphide. These are the 3 5 semiconductors. Not only these, people have also looked into 2 6 kind of the materials also. Means second row, second column of the periodic table and the sixth column of the periodic table. The materials were zinc oxide, zinc sulfide, zinc selleride, cadmium sulfide, cadmium selleride, cadmium telluride, right? So these are the 2 6 semiconductors also people are looking into. Not only these, people have also talked about the dichlorogenized materials also like molybdenum disulfide, right? So these are the different materials people are looking into because we'll have to address the scaling challenges for the new developments in the integrated circuits. So the approaches for the nano electronic devices were the first path. Already we have seen that first path was the solid state devices, and the second path for the innovation is the molecular electronics. So come up with the first path where people are talking about device architectures. Like I told you, there was bulk FETs were there, bulk planar were there, then double gate came, then tri-gate came, then quad gate came. Then people talk about gate all around. After gate all around, people come up with the FinFETs. Now people are talking about nanosheet transistors. So that were the solid state device level. Not only this, the second part would be people are talking about molecular electronics, where the atoms would be the work like a channel material for the molecular electronics. So when we talk about molecular electronics, the physics will be different. The physics will be quantum physics, and the theory would be density functional theory. So actually, for any material, when we innovate any material, people, device researcher would look for two important parameters. One would be the band gap, and the second one would be the effective mass. Once you know the band gap and the effective mass, then you could analyze this with the different model, come up with the device and then circuit and the system. Then that is another domain where people are working. But in future research, molecular electronics is the upcoming era where people are starting doing the research. And the promising nanoelectronic devices in the future computers will be nano CMOS, RTDs, and single electron transistors where it has the quantum effects. And for the molecular electronic side, people go with the molecular electronic resonance diode and the spintronics where people are trying to make up with the spin devices. My friends, I feel really very proud when any Indian name come in the research. Like when I see the approximations, like we know about the, in physics we have the Fermi Dirac approximation, right? Or you might have heard about the Bose Einstein approximation. When the name of the Satyendra Bose came to the with Einstein, I feel very proud because my Indian name is coming into the physics because Satyendra Bose was the researcher who come up with the Bose-Einstein approximation. Similarly, for the spintronics also now one name is upcoming in the spin era. That name is the Supriya Datta. I mean, you could Google it. You could go on the nanohub.org. He is the pioneer person. He come up with the new spin FET, and the name of that spin FET is Datta Das transistor. And now people are using the Datta transistor for spintronics applications also. So like this, our name should come up in the books or literature, so that we could say yes, we did something in our research or something in our research field or the technology innovation field. So these are the active research in nanoelectronics. As I so far I talk about nano CMOS, RTDs, resonant training diodes, single electron transistor, molecular devices, MRAM, hard drives. So Intel is worked on the nano CMOS, IBM is working on RTDs and single electron transistor. In all the domains almost. Lucent Technology is work on the single electron transistor. Seagate is working on MRAM. And these are the Purdue universities working on the MRAM. So these are the where the active research groups, those are working in the domain of the nano electronics. So, summarize of the talk for today would be, I will not take more time. What are the challenges for the nanoscale CMOS? So, the challenges would be high electric fields, power supply versus threshold voltage, as I told you, then heat dissipation, then like I told you in SOI, there is a one challenge is there that people call it as a self-heating effect. So, heat dissipation, interconnect delays, bulk properties. There are also open problems. How lithography is the open challenge now. How the nanometer, because the lithography is limited by the wavelength, right? So lithography is the e-beam lithography is the open challenge. Then how the new 3-5 semiconductors will come up, or even column 4 semiconductors will come up, like silicon germanium or gallium arsenide, and we'll have to come up with the new device architectures. And the carbon nanotubes is also one of the material which people are using. Flexible electronics is also one of the open era. My alma mater IIT Kanpur come up with the National Flex Center also. If some of you are interested, just mail me or ping me a message. I will try to make a contact with IIT Kanpur with the Flex Center, which is come up with the new era, that is the National Flexible Electronics Center. So you could address the flexible electronic challenges as well. The challenges would be again for the interconnects, then fabrication is also challenging. Open problems would be fabrication using DNA for self-assembly, then memory array for nanotubes, then how the carbon nanotubes could be used, or how to fabricate FPGAs using the carbon nanotubes. So far the FPGAs we are using, the prototype formation already you are doing, Xilinx FPGA like Spartan, Vertex, Altix, you are using. But can we able to develop the FPGAs with the carbon nanotubes? So again, there are fabrication challenges. These are open challenges which you would call, or we all could address. And again, there are challenge. A summary would be electrons combined like island. It's a kind of carbon nanotube or single electron transistor is like a island. Let us take one example. If there is a simple quantum dot, how I could make the interconnect connections with that carbon dot, right? You could not make, right? Imagine there is one carbon dot in front of you and you wanted to connect the electrodes, right, to this quantum dot. You could not. So that is what the Coulomb blockade concept came up. Tunneling came up. There are different challenges are there. So single electron transistor, quantum dot, quantum cellular automata, there are different devices people are making, different arrays are making by using the quantum electronics or quantum devices. But there are again open challenges and open problems also. As I told you, lithography was one of the challenge. Then we'll have to come up with the material synthesis we'll have to do. And obviously, so far in the VLSI domain, right, there was a traditional mechanism where we were talking about the speed, area, and the power, right? Speed, area, power. These were only the three constraints for the VLSI design engineers. But today, not only the traditional speed, power, area, one more challenge, one more mission has been added, and that mission challenge is the testing. Because we'll have to not only just develop the silicon chip, we'll have to test it also, right? Let us say I come up with a dual core processor today. I will send it for the foundry for tape out. But from the foundry, when the taped out chip came up, I'll have to test it. I'll have to assure myself that whatever design I send for the tape out in the foundry, when the chip will be coming, taped out chip will be coming, I'll have to test it, whether it is working like a processor which I send for the fabrication or not, right? So in silicon VLSI domain now, the upcoming challenge would be testing, because so complex device architectures we are developing, we are making integrated circuits, but how to test them? So testing is the another domain where people are doing research. My friends today in various industry, highly paid engineers are verification engineers because they have to use the stuck at fault models, and the open problem would be how the taped out chip at this nano dimension, which at the start of the talk I'm telling you how we are going to test the fabricated chip, which is in the molecular electronic domain, right? So these are the open challenges for this. So just advertisement I am doing now. This is my institute advertisement. So this is the A2D sim simulator tool. Proudly I would tell you that this tool is developed by my student Rajesh. He is working now in Micron. He completed his PhD. And we named the tool as a A2D sim. The name is Atom 2 Device Simulator. So we use the open source tool chain and we come up with the new device. That tool is available on the GitHub. You search it out, and this tool you could use for your device simulation as well. So we use the open source tools like Quantum Espresso, Vanilla 90, Nanotical Vidis, and we come up with the new open source tool. We name it as a A2D sim. And these are the kind of the some sensors which we have developed. As I told you, we are fabricating the sensors. So my domain of research is now on the soil sensors, because I thought, okay, why don't we address the social challenges now, because agriculture is the domain where lot of farmers has to go to test their soils in the soil laboratories, and soil laboratories are really very expensive. So I thought, why don't I come up with the any prototype system where the farmers could able to test the nitrate, potash, and the phosphate, right? So NPK soil sensors we trying to develop. This is the simple fabrication processes which you use, and now soon my student Gopal is deploying it our VNIT garden, where we are developed this. This is with the just gadget I'm showing you, which we are using for our soil sensing as well. So that's all from my side today. I hope you enjoyed my talk, and I tried my best to give you a lot of information which I had in my mind. So if you wanted to contact with me, free feel to call me, or on the send me the message or send the mail to me. My profile is there, and I'm again suggesting you all you just visit the nanohub.org website, which is a Purdue domain, Purdue website. You just visit it and try to make your own registration, do registration over there, and there are a lot of free tools are available to do your simulations. I know most of you are from the private institutions, and private institutions will not able to bear the cost of the tools which we are using at VNIT. So, but the open source tools are also available on the nanohub.org. Just download them, make your own registration, and try to use these talks and the tools for your research knowledge improvement. So that's all from my side. This open is forum for open questions now. You could ask me the questions if you have any question to you.
Awesome session,
Sir,
sir. Yes, it is open. You can
sir, good
unmute
evening,
and
sir.
yeah.
Sir, shall we design any circuit with the gate all-around FET using A2D sim, sir? That is your open source tool, sir.
Yes,
Shall we
yes,
simulate?
yes. You could able to design gate around Fate also with the open source tool which I told you, A2D sim.
Okay. Actually, we are already download NanoHub, sir. They are asking some license key. They are asking now, sir.
No, you just have to have the your own institute mail ID. The
Okay.
social media mail IDs they will not accept. If you have
Okay.
institute mail ID, they will register you on the NanoHub.
Okay. In that only if you are there, sir, to open source, or all are open source only. Some cadence tools are it is available, but it is not. It is asking some key.
On NanoHub, actually, you might have heard about the Chipping Center at SEDAC Bangalore. So
I know, sir. C2S.
yeah.
Sir.
So
Uh,
CDAC Bangalore is giving the even cadence synopsis mentor, even 2D ticket, 3D ticket, all licenses they are giving. So you could use that. And that
oh,
you could just send them the mail key, yes, we are running any VLSI program. Like today people are talking to develop the BTech in VLSI design, right? I mean
yes,
the
sir.
AICT also
Mm,
told. So
mm.
you could tell them to have these licenses.
Okay, sir. Thank you, sir. Very informative session, sir. We have learned many. Thank you, sir.
Okay, thank you.
We have one more question in the chat. They're asking Savaranan is asking for do we have the facility for implementing this CMOS technology for fabricating MEMS devices in India?
Yes, we have the MEMS centers here, not with the CMOS, but sensors we could fabricate. So if you talk about the CMOS and the MEMS together, in India we could not fabricate. In Japan there is one laboratory. You just Google it. That fellow will be providing the facility, Tanaka Laboratory. So that could be possible. But India CMOS MEMS we could not fabricate. But MEMS sensors we could develop.
Any more questions? You can unmute if you want.
Sir, I am Saravanan, Dr. Saravanan from Savita University, Chennai.
Yes, sir.
Yes, sir. Yes, sir. Thank you for your kind information, sir. What my actual question is, we have any facilities in Indian labs like DRDO or some other national institutes like device
Yes.
fabrications? Any device fabrications using this kind of techniques, modern electronic devices for especially for automobile sensors and transducers like that, sir? Or,
Yes, actually, now in India, we could not able to fabricate the technologies. I mean, 1.2 nanometer or
yes,
1.8
yes.
nanometer devices we could not fabricate.
Okay,
But the nanoscale MOSFETs we could fabricate. That is what now, as I told you, right?
yes,
In
sir.
2010, we have two INP centers, Indian Nano Electrons Users Program. One was at IIT Bombay
Yes,
and
sir.
one was at IC Bangalore.
Yes,
Now
sir.
they come up with the six total INP centers. That one is
Yes, yes.
there in IIT Bombay, IIC
Mm.
Bangalore, obviously. One is there in IIT Guwahati, IIT Chennai, and IIT Delhi.
Yes,
So,
sir.
so these centers are there for use of fabrication. So you not to do anything. I mean, you have to just write a research proposal. You
Okay,
have
sir.
to make your own login ID with the
Mm.
INP center. You have
Mm.
to send your proposal. They review it and then they ask you to give the fabrication facility to fabricate your devices.
Okay, sir. Why? Because I am asking is like our government of India now implementing the semiconductor. Now focused on semiconductor and many facilities are opening. Recently, our semiconducting materials, semiconducting device fabrications. Now India is focusing to invest more on this particular. Like before
True,
itself,
true,
it's a
true.
nano initiative, nanotechnology initiative, NNI something nation. Now
Yes,
we our India is focused on developing the semiconductor devices. Our own. Facility we are developing. I think it's in
correct,
initial
correct.
stage.
True, true. Like
Yes,
this now, there are total 10 firms. I mean, 10 different semiconductor firms are starting.
yes, sir.
Not only in Gujarat, Dholera
Yes,
and Sanand, right? There are 10 different places it has started. Even in Telangana also it started.
yes, sir. Yes, sir. Now Andhra Pradesh and Telangana now focused on quantum computing, and Telangana is now semiconductor fabrication. So Bangalore have a semiconducting companies. So now India is making initiative to produce and fabricate our own make. I mean make in India like that. So that's
Yes,
what
yes,
any implementation on national institute. That's what I'm asking, sir. Thank
yes,
you
yes.
very much.
Even I will appreciate the efforts that they have done by the Chandrababu Naidu.
Mm.
He's come up with the Quantum Valley at
Yes, sir.
Amravati.
Yes, sir. He also announced if anyone is working particularly on quantum computing and get a Nobel
Yes,
Prize, he is giving some much of crores as a remuneration like that, sir.
yes, yes,
So now
true.
India is very urging working on particular electronics devices, make in India type like that's what I am
Yes,
asking,
yes.
sir. Thank you.
And even since I'm a part of that committee, I
Okay,
will
okay,
tell you
sir.
the
Very nice.
efforts done by the government of Maharashtra also.
Okay,
So
sir.
government of Maharashtra is also these are openly I'm telling you all. So government of Maharashtra is also put the efforts to development of the quantum computing, I mean quantum era.
Yes.
So for one hub has been made. So the quantum hub would be ISER Pune,
Oh,
and there
okay.
are four institutions have been involved. One institution is Batu Lonere, second
Okay.
institute is VGTI Mumbai, third institution is COU Pune, and the fourth institution is VNIT Nagpur. So
No.
these four institutions are involved in the quantum era. I am a part of that quantum mission,
Nice to
and
hear, sir.
the
Congratulations, sir.
main institute would be ISER Pune.
Super, sir. Thank you, sir. Thank you for your kind
Yes.
information. Very
Thank you.
nice, sir. Thank you.
Yes, any more questions? No questions?
Good evening, sir.
Yes.
My name is Harinandan Singh, sir.
Yes, yes,
I
please.
recently, sir, I am assistant professor in the School of Engineering Information Technology from Sanskriti University.
Okay.
So I have a question, sir, that here we are dealing with the new specializations which are running nowadays, AI ML batch, students of the computer science branch. So can we suggest some topics or some programs can we suggested for the students of AI ML?
Regarding AI/ML, I mean, I will just tell you recently, there was one VLSI design conference. I was the chairman of the user design track. So in that, it has been told that AI/ML could be used for the VLSI designs. So VLSI design along with the AI/ML, that would be a very good domain for the students. So how AI/ML could be used for the VLSI applications? So that will be the
Okay.
very good,
Thank you, sir. Nice.
very good opportunity for the BTech students, particularly the new generation students, because how these AI/ML could be used.
Because sir, nowadays we are know that the interdisciplinary subjects are more important for the student also.
Yes. Yeah, that is what I mean.
Thank you for your suggestions.
Yeah, that is what I mean. The basic fundamental knowledge is required. Along with that basic fundamental knowledge, now
Yes.
I mean higher domain, whatever research is going on, that will have to deliver in the lectures.
Yes. Okay, sir. Thank you, sir. Thank you, sir, for your information.
Okay.
Any more questions? Okay. Uh, it's really a wow world which you took us. Really. So I feel I should express my vote of thanks now. So we extend our heartfelt gratitude, Dr. Ganesh Patil sir, our esteemed guest of honor and speaker for today's ATAL Faculty Development Program. Your expertise in device physics and modeling, novel nanoscale MOSFETs, analog and digital CMOS circuits, VLSI system design, and organic electronics took us far beyond the conventional thinking. By sharing your thought provoking research problems and further directions, you encouraged us to think out of box and explore unexplored dimensions of semiconductor research. The depth of detail with which you unfolded the concepts truly carried us into an oh my god world of VLSI waiting to be discovered. So, on behalf of the organizing committee, we sincerely thank you, sir, for an inspiring, eye-opening, and a memorable session. So, once again, uh, I don't have words because today you have like awakened us, and really, it is really very helpful. Like we will see that whatever little part, little contribution we will have, we will do our best, and we will see that this explores. And like you told, ki we Indians will be very proud of the contributions which we'll be doing in the VLSI world. So thank you once again, sir, for the inspiring session.
Ma'am, don't call me as a sir. I'm your student, ma'am.
No, but now with the knowledge you are having, I'm forced to call you sir because I never imagined. Like, I'm really very proud. Our institute is really very proud of having such alumni. You are assets to our engineering, sir. Really, hands off and hats off to you, sir.
Thank you, thank
Thank
you.
you. Thank you very
I
much.
just wanted to tell to the audience, actually,
Yes.
when I was in SVPM COE Malegaon College, right? And I was taking my elective course as a VLSI design,
Mhm.
and ma'am given me the opportunity to take that VLSI design course. Ma'am, thankful
Yeah.
to you, ma'am. You have given the opportunity to take me VLSI design course, and now the
Yeah.
output is in front of you.
Right. I forced a correct person. I just nurtured a very good seed in you, the of VLSI, in which I'm seeing you are blooming and blooming. Thank you for that. Thank
Thank you
you.
very much, ma'am. Thank you. Thank you,
Okay,
all the
chalo.
audience, for your patience listening.
No, it was not. They were like no one just blinked their eyes. Everyone was just listening. What next? What next? What next? We were in that mood. Thank you. Thank you once again.
Thank you, ma'am.
You can see the chats and all that. Like, really, I'm very proud, and our institute is very proud to have you as an alumni, the asset of SVPM COE.
Thank you, ma'am.
Okay, chalo, we'll be in touch. I'll be sending more aspiring SVPM COE guys to you to groom for.
Yes, yes, yes. Thank you,
Okay.
ma'am. Now I'm closing the meeting.
Yes, sure, sure.
Thank you, ma'am.
Thank you. I hope all of you are feeling the feedback forms. Okay, sir, we'll leave the session.